এটা লাইভটা শুরু হয়, হ্যাঁ লাইভটা শুরু হয়নি, লাইভ শুরু হলে আমি ওইটা দিচ্ছি। হ্যাঁ আমি দেখলাম আর কি।
লাইভ দেখাচ্ছে তো, শুরু হয়ে গেছে দেখাচ্ছে তো।
আরে তাহলে শুরু করুন, তাহলে আমার এটাতে হ্যাঁ শুরু করুন।
তো শুরু করে দেবো।
হ্যাঁ
থ্যাংক ইউ ডক্টর মানিক বিশ্বাস। Greetings to one and all. First of all, I want to take a moment to thank our respected principal sir and the IQAC coordinator for endowing me an opportunity to share this morning with all of you. I am Joydeep Chakraborty, Assistant Professor of Mathematics of Nagar College. I am glad to welcome all the virtual participants, distinguished delegates, and honorable speakers in this international level webinar on behalf of Nagar College family. This venture is like a virtual vigor for us to consolidate our academic existence. It is an opportune moment to refresh our knowledge in all the fields, especially abstract algebra, algebraic topology, and differential geometry related to the recent trends in mathematics. The webinar schedule brushes upon a spectrum of exciting and benefiting themes that disseminates methodologies and aspects to unfold the recent trends in mathematics. Last but not least, I extend my gratitude to our technical support team and entire Nagar College family for being there to make this event a success. Now I transit this virtual space to our principal to spare some of his valuable words in this occasion. It's over to you, sir. Principal sir, I am requesting you to deliver some talks on this topic.
Webinar Organizing Committee, Sri Convener, Sri Somen Pradhan, Secretary Sri Joydeep Chakraborty, other members Jalaluddin Mondol, Joydeep Sinha for organizing this webinar. I would like to welcome distinguished speakers, Dr. Sushan Kaur, Professor, Math Department, Jadavpur University, Dr. Pradeep Machi, Professor, Math Department, Calcutta University, and Dr. Surojit Ghosh, University of Haifa, Israel, who, cutting their busy schedule, spare their valuable time with us only in view of sharing views on recent trends on mathematics they notice, thus including audiences joining with us through organizing committee provided various links. Especially thanks to all audience without whom no webinars can reach to its cherished goal. Last but not least, I convey my best wishes to Nagar College staff, Sudipto Shao, Assistant Professor in Bengali, IKC Coordinator, Dr. Manik Vishar, Assistant Professor in Bengali, Tokipur Rahman, office staff, and others, who, by extending their cooperation and earnest labor, bring this seminar into reality. I am sure that this webinar will be enriching and beneficial to all participants of this program. I conclude my talk by congratulating all of you once again and wishing you all the best for a successful completion of this webinar. Thank you. Over to Jaideep Chakraborty. I am not audible. Please, Jaideep. I end my talking. Can you hear
জয়দীপদা
me?
আনমিউট করো। জয়দীপদা
I
আনমিউট
am
করো।
requesting Dr. Sudipto Shau, IQAP coordinator and Dear Council Secretary of our college, to deliver his feelings in this occasion.
Thank you, Sri Jaydeep Chakraborty, to give opportunity to speak something here. At first, I think our mathematics department, Nagar College, has organized interesting say webinar, one-day international webinar on recent trends in mathematics. I want to congratulate every members of the mathematics department. Sri Chakraborty already told that the aims and objectives of this webinar, I do not repeat. I convey my heartfelt gratitude to all listeners, all faculty members, all of our students. This is very interesting topic. I hope the grant this will be very interesting for them, and I wish the grand success of this webinar. And I convey my gratitude to the all panelists, Dr. Sukhendu Kaur, Dr. Pradeep Majhi, Dr. Surojit Ghosh also, and I convey my thank you to Sri Shoumen Pradhan, Sri Jaydeep Chakraborty, my esteemed colleague, and once again I wish grand success of this webinar and wish all of you and very enjoy it. Now I over to the microphone, Sri Jaydeep Chakraborty.
Thank you, Dr. Sudipto Shau, to deliver his important speech and feelings today, this very important day. Now, it is our pleasure that Mathematics Department of Nagar College has organized two webinars, one national level and other is international level, in 2 successive weeks. And I think this is the first time in 22 years venture of Nagar College family. Now, I can say that in the mathematics has total 2700 branches, in which abstract algebra is the most modern topic in the algebraic sphere of mathematics. Today we shall share our idea in abstract algebra from Dr. Sukhendu Kaur, Professor of Mathematics, Jadavpur University. His topic is related to the abstract algebra. Dr. Kaur has completed his MSc degree and awarded PhD degree from University of Calcutta, and he has published near about 70 research papers in different reputed journals. He also visited Hong Kong, Indonesia, Thailand, Vietnam, etc. to deliver his invited lectures. Now I am requesting Dr. Sukhendu Kaur to deliver his speech in this occasion. Thank you, sir.
Thank you. Thank you to all of you. I have to present my this. Is it visible to all of you?
Yes, sir. Visible.
As per you.
Yeah. Good morning to all of you. First of all, I would like to thank the organizers, especially to uh, Somen Pradhan and Joydeep Chakraborty and all the faculty members of mathematics and all the faculty of Nagar College and the principal sir for inviting me and to give this opportunity to deliver this lecture. Now, the title of my lecture is An Deep Introduction to Ternary Algebraic Structures. Basically, in our undergraduate and postgraduate syllabus, we know about the binary algebraic structures. And there are so many binary algebraic structure. One is the semi-group, another is the group, another is ring, fields, vector space, like that. And all these algebraic structures are in the binary operation settings. Now, binary operation means what? A binary operation is nothing but a mapping from a non-empty set S cross S to S. It is nothing but a mapping from the Cartesian product set S cross S to S. Now, we know that semi-group is nothing but a single composition algebraic structure, which is a binary single composition algebraic structure satisfying only associative property. And group is a single composition algebraic structure which satisfies the associative property, which contains identity element and the inverse property. Now, if we just if you take any ring structure means it is a double composition algebraic structure. That means in that case it is a non-empty set together with two binary operations. And normally we take this addition and multiplication as the two binary operations. Because in our school days, if we look into the set of integers, all of us familiar with two binary operations. One is addition and another is multiplication. These two are common to binary operation in our school days, and all of we are doing by elementary operations on integers. And all of you know that with respect to binary addition and multiplication, the set of integers forms a ring, and this ring is called a ring of integers. Now, if we forget about the product, the multiplication, then with respect to addition, this integer set forms a group, Z plus forms a group. So from our school days, we know this type of algebraic structure. Sorry. Now, if we now my topic is the ternary algebraic structure. Now, what is the necessity of the ternary algebraic structure? Why we can study the ternary algebraic structure instead of binary algebraic structure? Basically, if we take the positive integer set, then with respect to addition and multiplication, it forms a certain type of binary algebraic structure, double composition binary algebraic structure. But if we take the negative integer set, then we see that this is not close with respect to binary product. If we take two negative integer, then the product of two negative integer is again a positive integer. Then we cannot have any binary algebraic structure on the negative integer set with respect to binary product. But if we take three negative integers, and if we product these three negative integers, then we can find another negative integers. That is, it is the set of negative integers is close with respect to ternary product. Ternary operation means what? This is nothing but a mapping from S cross S cross S to S. We can also generalize this operation to n-ary structure also. But throughout our lecture, I shall confine myself to ternary operation only. Now, there are so many other sets, collection of elements which do not form a binary algebraic structures. We provide some examples of that sets which do not form any binary algebraic structure. But these sets certainly forms a ternary algebraic structures. That's why we are going to introduce a new type of algebraic structures which are generalization of binary algebraic structure like that. Now, the outline of my talk is, first I want to give some introductory idea about the ternary semigroup and ternary group. All of you know what does it mean by a semigroup, what does it mean by a group. I just like to generalize these things in the settings of ternary operations. Then I would like to introduce about what does it mean by a ternary ring and ternary semi-ring. We know that what does it mean by a ring. I just generalize this ring settings to binary operation to ternary operation to a ternary ring. And a semi-ring is nothing but a generalization of ring and the distributive lattices. I want to introduce the notion of ternary semi-ring also, which is the generalization of semi-ring. And then I give some introductory idea about certain classes of ternary semigroups and semi-rings. If time provides, I give some problems associated with ternary algebra structures, some research problems which can be taken about for future research, some problems associated with ternary algebraic systems, and finally I conclude my lecture. This is the brief outline of my talk. Now I first give some introductory idea about the literature of the ternary algebraic structures. The introduction of mathematical literature of ternary algebraic systems, this is that has a long history, because already we have in the literature of ternary algebraic system, the notion of ternary semigroup, the notion of ternary group, the notion of ternary ring are already have introduced by many mathematicians. We have also introduced the notion of ternary semi-ring in 2003, generalizing these semi-ring notions. Now, the notion of ternary semigroup was known to as Bunner. The Bunner first introduced this type of ternary semigroups, which is a generalization of the semigroup theory. Semigroup is a single composition algebraic structure which satisfies the binary associative law. Here we shall see that ternary semigroup is a algebraic structure with respect to ternary operations which satisfies ternary associative law. Now, after the introduction of ternary semigroup theory, in 1965, F.M. Searson started the notion of ideal theory of ternary semigroups. We are all familiar with the notion of ideal in ring theory. This notion of ideal of ring theory can be generalized in semigroup theory also. And this notion was started by F.M. Searson in ternary semigroup theory. Now, after long back in 2010, M.L. Santiago and Professor S. Srivala from Madras University, from Ramanujan Institute of Advanced Study, they published a paper in Semigroup Forum and about the regular ternary semigroup theory. Now I give the formal definition of ternary semigroups. Any non-empty set S together with a ternary multiplication, that means is a multiplication means ternary multiplication is a mapping from S cross S cross S to S. It's called a ternary semigroup if this satisfies this type of ternary associative law. Then we say that S is a ternary semigroup. A semigroup means it is a non-empty set. Together with a binary product, this satisfies binary associative law. And ternary semigroup means it is a non-empty set together with a ternary multiplication which satisfies this type of ternary associative law. Now, another well-known results are from group theory. All of you know the notion and the familiar theorem, the Calis theorem, which is nothing but a representation theory of group structure. It is a very well-known and familiar theorem in group theory. Now, this result can be generalized to semi-group theory also. Calis theorem, what does Calis theorem means? Every group can be treated as a isomorphic to some subgroup of the symmetric group or permutation groups. This. Now, in semi-group theory also, we can generalize this notion. If we take the collection of self maps, if you take any non-empty set X and take a mapping from X to X itself, then collection of all those mappings with respect to mapping compositions always forms a semi-group. That means this mapping composition always satisfies the binary associative law, that is F compose G compose H is always satisfies the F compose G compose H because the mapping composition is always associative. Therefore, this forms a semi-group. This semi-group is called a semi-group of mappings or semi-group of transformations. Now, we can show that any semi-group can be embedded in semi-group of transformations. This is nothing but the generalization of the Calis theory in semi-group theory. Now, we want to give some parallel analog in ternary semi-group theory also. For this, we have to introduce the notion of what does it mean by ternary semi-group of mappings. For this, we just take this Txy is the set of all mappings, which is a mapping from X to Y, where X is a non-empty set and Y is a non-empty set, and take the collection of all mappings from X to Y. Now, we take the set this Txy, this is a collection of all mappings from Y to X. Then we take the Cartesian product set this. This Txy means this is the Cartesian product of this Txy is a collection of all mappings from X to Y, and this is the collection of all mappings from Y to X. Now, we can define a ternary multiplication on this set by this way. Define a ternary multiplication on Txy as follows. F1, G1, this is a Cartesian product set, therefore this contains all ordered pair of elements F1, G1 like Fg, where F belongs to this and G belongs to this. Now we take this product, this ternary product, this is F1, G1, F2, G2 and F3, G3. Mind that this is not a component-wise product, because the component-wise product here is not defined, because the F1, F2, F3 cannot be defined, because F1, F2, F3 are all mappings from X to Y. We cannot composite these three mappings because all are the domain set is X and codomain set is Y. But we can define this product like this, F1, G2 and F3. Then this is a mapping from X to Y again. This F1, G2, F3 is a mapping from X to Y. Again, we can define this G1, F2 and G3. Then this is a mapping from Y to X. Then we can define this ternary product by this way. With respect to this ternary product, this Txy set forms a ternary semigroup. This Txy forms a ternary semigroup, and this ternary semigroup is known as the ternary semigroup of mappings. This type of ternary semigroup is called a ternary semigroup of mappings. And it can be shown that any ternary semigroup can be embedded in a ternary semigroup of mappings. Now, we can generalize this notion in the matrices also. This notion can be generalized to matrices also. If we take the collection of matrices, this M by N matrices, the set of all M by N matrices over a field F, and if we take another collection of N by M matrices over the field F, And if we take this Cartesian product set this, the M is equal to the Cartesian product of set this M by N collection of all M by N matrices, and this is the collection of all N by M matrices. And we can define a ternary multiplication on this set by this way. Again, this parallel to that mapping, this A1, B1, A2, B2, and A3, B3 is, mind that this is not also the component-wise product. This is A1, B2, A3, and this is B1, A2, B3. Mind that if you take this component-wise product A1, A2, A3, then this product is not defined, because this is a M by N matrix, this is a N by N matrix, therefore this product cannot be defined. But certainly this is a M by N matrix and this is a N by N matrix. Therefore this product is defined, and with respect to this ternary product, one can easily check that this forms a ternary semigroup. This semigroup is known as the ternary semigroup of matrices. Now both these notions were introduced by A. Chudovsky, this notion of ternary semigroup of mappings and ternary semigroup of matrices. Now, in the literature of ternary algebraic structure, the notion of ternary groups also introduced by D.H. Lemmer in 1932. D.H. Lemmer investigated certain ternary algebraic systems which called the triplexes, and this can be turned out to be the commutative ternary groups. Now, these ternary groups are the special case of another notion which is called the polyadic groups. This polyadic group, also known as the N groups in another terminology, this notion was introduced by E.L. Post. Now, according to D.H. Lemmer, he defined the notion of ternary groups by like this way. A ternary semigroup S is called a ternary group if for any ABC belongs to S, the equation, these three equations have unique solution. This is ABX equal to C, AYB equal to C, and ZAB equal to C have unique solution in S. Then we say that it is a generalization of the semigroup theory. A semigroup S is said to be a group if you take any ABC belongs to this, any AB belongs to G, such that any AB belongs to S, such that AX equal to B and YA equal to B. These two equations have solution. In semigroup theory also this can be treated as the group if these two equations have unique solution. And this is the generalization of that notion in ternary group theory. Now, in the literature of ternary algebraic system, also ternary ring also introduced by W.G. Lister. In 1971, W.G. Lister published a paper in the Transaction of American Mathematical Society. In that paper, he introduced the notion of ternary rings, which is nothing but the generalization of the binary rings. Now, what does it mean by a binary ring? Binary ring and a ring, or if you take the ring of integers Z plus dot, like that, if you take any non-empty set R together with two binary operations, addition and multiplication, then ring means what? This R plus is a commutative group, R dot is a semi-group, and two distributive property holds. This left distributive property and right distributive property. This distributive property is nothing but the connection between the two binary operations, addition and multiplication. Now, Lister generalized this notion to a ternary ring. Now, ternary ring is nothing but an algebraic system consisting of a non-empty set T together with a binary operation called addition. Mind that this addition is a binary operation and product is the multiplication is a ternary operation, and which with respect to addition this forms a commutative group, and with respect to multiplication this forms a ternary semigroup. And if T satisfies this left distributive property, right distributive property, and the lateral distributive property, because it's a ternary algebraic structure, here three distributive laws holds with respect to binary addition and ternary multiplication. This type of algebraic structure known as ternary ring. Now, the notion of semi-ring was first introduced by H.S. Vandiver in 1934. semi-ring is nothing but the generalization of ring and distributive lattices. Now, what does it mean by a semi-ring? If you take the ring of integers z plus dot, and if you take the positive integers say z plus, then z plus cannot form a ring because additively this does not form a group. But z plus certainly forms a algebraic structure. With respect to addition, this forms a semigroup. With respect to multiplication, this forms a semigroup. And to distributive property holds. This is our basic natural algebraic structure on natural numbers. Basically, if you take the natural positive integer set, means it's a natural number set. In the natural number set, we can define this type of algebraic structure, and the natural number set is the common notion of semi-ring. This is not a ring, but this forms a semi-ring. And mind that this natural number set have another important property, which is the cancellation property. Mind that this is not a ring, but these have cancellation property. This is a semi-ring structure with cancellation property. And natural numbers are very important to us because once Kronecker remarked that God created natural numbers and everything else is man's handiwork. We don't know who created natural numbers, and that's why Kronecker remarked that the God created natural numbers and everything else is man's handiwork, and everything else is created by man. Now, this natural number is a natural example of semi-ring. Now, semi-ring is nothing but a non-empty set S together with two binary operation addition and multiplication, with respect to which S plus forms a commutative semigroup, S dot forms a semigroup, and two distributive laws holds, left distributive laws and right distributive laws. Now, I have already mentioned that this positive integer set together with usual binary addition and multiplication, this forms a semi-ring. Mind that this does not form a ring, but this forms a semi-ring. Now, if we look at the negative integer set, this z minus, then I have already mentioned that this z minus is not closed with respect to binary product, but it is closed with respect to ternary product. Because if you take any c negative integer, then the product of this c negative integer is again a negative integer. Now, we can also see that this negative integer say z minus with respect to a binary addition and a ternary multiplication, this forms this satisfies this property. This z minus with respect to addition forms a commutative semigroup. Z minus satisfies this type of ternary associative law, and Z minus satisfies these three distributive property. This left distributive laws, this is lateral distributive laws, and this is right distributive laws. Because this product is a ternary multiplication, therefore here three distributive laws are there. One is left distributive laws, another is lateral distributive laws, and another is the right distributive laws. Now notice the above fact in the negative integer set z minus. In 2003, myself and my respected supervisor, Professor T.K. Datta, have introduced the notion of ternary semi-ring, which is a generalization of the notion of ternary ring introduced by W.G. Lister in 1971. This ternary semi-ring is nothing but a generalization of the notion of ternary ring, and also the generalization of the semi-ring also. Now, if we look at the ring of integers, then we can see that the subset z plus of positive integers forms a semi-ring, whereas the subset z minus of negative integers forms a ternary semi-ring. If we look at this ring of integer z plus, then if we take this positive integer set with respect to usual addition, binary addition and binary multiplication, then this forms a semi-ring. But if we take this negative integer set with respect to binary addition, and this is ternary multiplication, mind that this is not binary multiplication, this is a ternary multiplication, then this negative integer set with respect to usual binary addition and ternary multiplication, this forms a new type of algebraic structure. This is called ternary semi-ring. Now, in general, if we take a partially ordered ring, then we can see that its positive cone forms a semi-ring, whereas its negative cone forms a ternary semi-ring. If you take any partially ordered ring, this partially ordered ring means it is a ring structure together with a partially ordered relation. This. With respect to that partially ordered relation, this ring is partially ordered ring. Now, if you take this, the positive cone of this is the semi-ring, this forms a semi-ring. And if you take the negative cone of this forms a ternary semi-ring. Now, the results in ordinary semi-rings, if you take any results in any ordinary semi-ring or any ordinary binary algebraic structure may be extended to n-ary algebraic structures. But mind that for arbitrary n, the transition from n equal to c to arbitrary n entails a great degree of complexity that makes it undesirable for exposition. And that's why we shall confine ourselves in the present talk wholly to ternary algebraic structures only. Now, I want to give the formal definition of ternary semi-ring. This is the formal definition of ternary semi-ring. Formal definition means that if you take any non-empty set S together with a binary addition and the ternary multiplication, then this non-empty set S, this is called a ternary semi-ring. If S plus is a commutative semigroup, if S satisfies this type of ternary associative law, and this three distributive property holds. One is the left distributive law, this is the right distributive law, and this is the lateral distributive law, and this is the right distributive law. This is nothing but the generalization of the notion of ternary ring and also semi-ring also. Now, in other words, S plus dot is said to be ternary semi-ring if S plus is a commutative semigroup, S dot is a semigroup, S dot is a ternary semigroup because this dot is a multiplication, this product is a ternary multiplication. Mind that this is not a binary multiplication, this is a ternary multiplication. With respect to that, this forms a ternary semigroup and three distributive property holds. The left, lateral, and right distributive property holds. Now, I want to give some another examples of ternary algebraic structures. Mind that if we can look about this set, this R root 2, where R is any rational number, then you can easily verify that this cannot be a product of two numbers like this. This cannot be a binary product. It is not close with respect to binary product. But we can easily see that this set is close with respect to ternary product. Therefore, S1 forms a ternary semi-ring together with usual binary addition and ternary multiplication. The binary addition and ternary multiplication. Now, if you take this set S2 equal to this Ri, where R is any real number and I is any imaginary number, this, then again you can see that this set is not close with respect to binary product, but this set is close with respect to ternary product. Therefore, S2 forms a ternary semi-ring with respect to usual binary addition and ternary multiplication. Now, take the set SC with the set of all functions like this, x to r minus, where this is a negative real number set and x is any non-empty set. Then if you take the collection of all mappings and if we define the binary addition by this way, f plus gx equal to fx plus gx, and the ternary multiplication by this way, f gx equal to fx into gx into h. Mind that this is not a mapping composition. This is the component-wise the product. Mind that. With respect to mapping composition, this does not form a semi-ring. But if you take this product like this, fx into gx into hx, then this SC forms a ternary semi-ring with respect to this binary addition and this ternary multiplication. Now we can remark that the positive real valued function form a semi-ring, whereas the negative real valued function form a ternary semi-ring. If we take the positive real valued function, then this forms a semi-ring, and the negative real valued function forms a ternary semi-ring. Now we can also generalize the notion of ideals of rings in ideals in semi-ring, also in ideals in semi-group theory like that. Here we just give the formal definition of ideal like this. A left ideal means an additive. This is a ternary operation. Therefore, the additive subsemi group I of a ternary semi-ring is called a left ideal. If this satisfies this SSI, it's subset of I. In ring theory, this is Ri contained in I. And since it is a ternary algebraic structure, therefore this is SSI is contained in I. Lateral ideal of this is means this is lateral ideal of S if SIS is contained in I. Because this is a ternary algebraic structure, this new notion of ideal can be derived from this ternary algebraic structure. Mind that this lateral ideal concept does not arise in ring theory or any binary algebraic structure. But this notion can be derived from this ternary algebraic structures. Also a right ideal of S if this ISS is contained in I. Now ideal means it is a left ideal as well as a right ideal as well as lateral ideal of S. Then we say that this is an ideal of the ternary semi-ring S. Now S be any ternary semi-ring and A belongs to S. What does it mean by the concept of principal ideal in ternary semi-ring? We know that the notion of principal ideal in ring theory also, and principal ideal plays an important role in ring theory. We know that an important class of ring which is called a principal ideal domain. There are so many domains in ring theory, some integral domains in your undergraduate. Now it is a UGC syllabus, it's an undergraduate class. There are so many domains are there. One is the Euclidean domain, the principal ideal domain, the unique factorization domain like that. Principal ideal domains is nothing but an integral domain in which every ideal is a principal ideal. And ring of integers is a natural example of principal ideal domain because in the ring of integer set, every ideal is like the form nz where n is any natural number or 0. Then every ideal is a principal ideal generated by n, the natural number n, and every ideal is principal ideal. Certainly z plus dot is an integral domain, therefore this is a principal ideal domain. Now this principal ideal concept is very important in ring theory. We can also generalize in ternary semi-ring theory like that. This is a left ideal generated by A means this, right ideal generated by A means this. We can prove this result like that. The lateral ideal generated by this means this. And the ideal generated by A, this principal ideal generated by A means this structure. This. Now there are another notion of ideal. This is known as the K ideal in semi-ring theory. Now what does it mean by the K ideal stands for? We know that all of we know that in ring theory, every ideal is always a kernel of some ring homomorphism. Certainly a kernel of a ring homomorphism is always forms an ideal of a ring, and the converse is also true. That means if you take any ideal, then this can be treated as the kernel of some ring homomorphism. But mind that this result does not always hold in semi-ring theory. In semi-ring theory, every ideal cannot be represented as the kernel of some semi-ring homomorphism. And that's why here new class of ideals are there which are known as the K ideals. This K ideals means nothing but the those class of ideals which are represented by the kernel of some semi-ring homomorphism. And that's why this K stands for the kernel like this, the K ideals in this. A left, right, and lateral ideal I of a ternary semi, we can generalize this notion in ternary semi-ring like this way. K ideal means this x plus y belongs to y and x belongs to s, y belongs to y, imply that x belongs to y. Now we can also define another notion. This is called K closure of A. This K closure of A defined by this way, all those elements A belongs to S. such that A plus B equal to C for some BC belongs to A. Now we can show that this any ideal A is a K ideal of the semi-ring S or the ternary semi-ring S if and only if A equal to the K closure of A bar. This A equal to A bar, then we say that A is a K ideal of that semi-ring also. We can show this. Now another important class of rings which are known as the regular ring. Now how it is important in ring theory? The regular ring is very important class of ring in ring theory. Because we know that if you take the Cartesian product of two groups, then the direct product of two groups forms a group. If you take direct product of two rings, then direct product of two rings is again a ring. Now the natural question arises, if we take the direct product of two fields, now what can I say about the direct product of two fields? Now in fields, mind that fields is nothing but a double composition algebraic structures in which our basic four operations can be basic four algebraic operations. One is the addition, multiplication, subtraction and division. These four operations can be performed in those algebraic structures. These are known as fields. Or real number set is a natural example of a field. A rational number set, complex number set, all are forms of field with respect to usual binary addition and multiplication. And mind that all those three well-known sets, this rational number set, the real number set and complex number set forms a field. But mind that real number set algebraically not only a field, it is an order field. Not only an order field, it is a complete Archimedean order field. But mind that for complex number, this is a complete field, but this cannot be an order field. For rational number field, this is an order field, but this cannot be a complete field. Completeness property is not there. And that's why in respect of analysis, the real analysis is so much rich because the real number set is not only a field, it's a complete Archimedean order field. And that's why we can generalize many things in real analysis. But in complex analysis, parallel to that real analysis, if we go to the complex analysis, mind that in complex analysis, this complex numbers forms a field. This is a complete field, but mind that this is not an order field. The order property is not there. And that's why there are many things are lacking in the complex analysis. For example, if you take any, in the real analysis, the Rolle's theorem is there. But mind that in complex analysis, that there is no parallel analog of Rolle's theorem, because in complex, the Rolle's theorem, to prove the Rolle's theorem, the order property of real number very much needed. And since the order property does not arise in complex number, and that's why this parallel analog of Rolle's theorem or the mean value theorem like that, it cannot be held in complex analysis. Therefore, the field theory has important role in analysis theory to define the derivative of a function like that. Because for single variable function, the field theory plays an important, for real analysis, we can define the derivative as the division of two real numbers like that, fx minus fa by x minus a like that. But in R2, mind that whenever you goes to R2, not complex number, this R2 means two-dimensional plane, this R2 does not form a field. That's why in R2 we cannot have the differentiation or limit like that. This notion of limiting concept or differentiation is very much different from the complex analysis.
Sir.
Yeah.
Sir,
Yeah.
10 minutes left.
Okay. And that's why if you take the direct product of two fields, then you cannot show that this direct product of two fields cannot be a field, because F1, if F1 is a field and F2 is another field, then direct product F1 cross F2 contains divisor of 0. Because if you take 1, 0 and 0, 1, then the product is 0, 0. It contains divisor of 0. Therefore, direct product of two fields cannot be a field. But mind that direct product of field has important property like that. If you take the order property AB, then certainly there always exists another element xy such that AB, xy, AB is always equal to AB. You can take this x is the inverse of A and B as the inverse, y is the inverse of B, because these are the fields. If you take any non-zero AB, then always inverse exists because A belongs to some field, B belongs to some field. That means in that case, ABA equal to A, this property holds. This in any class of rings, if this property holds for every A belongs to R, if there exists another element X such that ABA, AXA equal to A holds, then we say that this is a regular ring. The direct product of two fields is always forms a regular ring, but this is not a field. Every field is a regular ring, but a regular ring does not always forms a field. So the regular ring is the generalization of the regular. This studied the regular ring by this way. We can study this regular ternary ring also. This notion was introduced in 2003 by T. Vasile. This introduced the notion regular ternary semi-ring, and this regular ternary semi-ring can be introduced by this way. And we can just keep this result. We can characterize this regular ternary semi-ring in respect of this ideal theory by this way. Now, S. Bonnet also defined another class of ring which is called the K-regular semi-ring, and this notion is defined by this way: A plus AYA equal to AXA. Mind that if it is a ring, then if you take this AYA in that side, then A equal to again AXA, like this is a regular ring. Now the von Neumann regularity and the Bonnet regularity can be coincide in any ring, but in semi-ring these two notions does not always coincide. That's why this distinguish the notion of Bonnet regularity and von Neumann regularity. It was renamed as K regularity, and the K regularity was extensively studied by Professor M. K. Sen and A. K. Bhuiyan. Now we can define the K-regular ternary semi-ring by this way. We can also have some results of like this. Is an example we can skip because due to the lack of time, we can skip this result. We can characterize the K-regular semi-ring by this way. I just skip this. Now I want to give some another notion which is called power ternary semi-ring. It's an important class of semi-ring. We can also define the power semi-ring, the power semi-group like that, and we can generalize this notion in power ternary semi-ring. The notion of ternary semi-ring comes out from the notion of ternary semi-group as follows. Power ternary semi-ring we can define if you take SB any ternary semi-group, PS take the collection of all non-empty subsets of beds. You can take also empty set, does not matter anything. Now binary addition is like this: A plus U plus B equal to U union B, and product is defined by this way: ABC, where A belongs to U, B belongs to B, and C belongs to this. Then with respect to this binary addition and ternary multiplication, this forms a ternary semi-ring. This is called the power ternary semi-ring. Now we can show that this result, important result, this power ternary semi-ring PS is a K-regular ternary semi-ring if and only base is a regular ternary semi-ring. It would be interesting to study different classes of power ternary semi-rings with the help of corresponding classes of ternary semi-groups also. Now I want to give some problems of ternary semi-group, ternary algebraic structures. Those who are interested, you can also study these problems. There are another important subject that has attracted the attention of semi-group theorists. If S1 and S2 are isomorphic semi-groups, then their corresponding power semi-groups, these PS1 and PS2, are obviously isomorphic. Now, quite natural to ask whether the converse is true. That means if PS1 is isomorphic to PS2, then could it imply that this S1 is isomorphic to S2? If the class C of algebra has this property, then we say that C is a globally determined class. Now, it could be an interesting problem to study the class of ternary semi-rings or ternary semi-groups which are globally determined. Now, there are also some problems if you take this ternary semigroup of mappings, this Tx, Y set, if you take the collection of all linear, if you take this X and Y are vector spaces and take the collection of all linear transformation from X to Y, and if you take the collection of all continuous linear transformation from X to Y, if you take this topological vector space like that, then it will be more interesting to study the ternary linear algebra of linear mappings and the non-ternary linear algebra of continuous linear mappings. There are so many problems in these ternary algebraic systems. You can, those who are interested, you can study this ternary algebraic structure like that. We can also study the notion of topological ternary semigroup of mappings like that. Now, taking into the foregoing consideration, it will be interesting to note that the results of ternary semigroup of matrices will be immediate consequence of the results obtained in the ternary semigroup of mappings. I just give an example. All of you know that if you take a square matrix, this is invertible if and only if it is non-singular. Now we know that the square matrices are invertible only. But whenever you take the rectangular matrices, these matrices are rectangular, class of rectangular matrices can be also invertible in certain sense. The inverse of rectangular matrices are known as the generalized inverse or G inverse of A. If you take this A and B belongs to this set, this is called idempotent if and only if this B is a G inverse of A and A is a G inverse of A. What does it mean by G inverse? An element, this A is a M by N matrix is said to have a generalized inverse or G inverse if there is another matrix B of order N by M such that this property holds, this A, B, A equal to A. Then we say that A has generalized inverse B. Mind that compared to the inverse of a square matrix, the generalized inverse may not be unique. The inverse of a square matrix is always unique, but this generalized inverse may not be unique. This has infinitely many generalized inverses like that. Now I conclude my lecture. Natural question arises why we can study the ternary algebraic structure. Our binary algebraic structure is sufficient to study in modern algebra like that. Why can we study the ternary algebraic structures? Now, I have seen many papers of ternary algebraic structures, and these ternary algebraic structures appear more or less naturally in various domains of theoretical and mathematical physics. And there is a mechanics known as Nambu mechanics. This is one type of ternary. This ternary algebraic structure can be dealt in Nambu mechanics. Nambu is a Japanese physicist in which the name as Nambu mechanics. This Nambu mechanics deals with the ternary algebraic structures like that. And I can also see the paper this sorry. Richard Kerner published a paper, Ternary Algebraic Structures and their application in physics. In this paper, they give a shortened overview of ternary ideas in mathematical physics. So we believe that many interesting applications of ternary algebraic structure in many areas of sciences are still ahead of us. Now, these are the references, some of my references of this and another this. Thank you very much for your listening. Okay, hope I can finish my lecture in due time.
Now,
okay, thank you. If you have any questions, you can
now
feel
we
free
can
to ask me.
now we shall discuss if there is any questions to Professor Shukendukar. Somen, is there any question to Professor Shukendukar?
Not now.
Yeah. Somen,
Projit?
can you hear me?
Yes.
Yeah.
Yeah,
Okay.
you are audible.
Thank you, sir.
Yeah. So I have few questions. Like,
Thank you, sir, for your valuable lecture and on a very interesting topic, ternary algebraic structure. It is a new branch or new idea in the abstract algebra branch. Thank you very much, and I shall put a appeal or proposal to Professor Shukendukar if he can give the copy of his lecture to upgrade us and to study his lecture very intensively. if he can give a copy of his lecture to us.
Jadidda,
Sir?
I have one question.
Yes.
Yeah.
Most welcome, Surajit. Most welcome.
Yeah, first of all, as you said that if you start with any ternary semi-ring or semi-group, you can embed in the mapping kind of semi-ring, right? Mapping kind of ternary semi-group, right? I don't know. Yeah, Sukhendu sir, can you hear me? Hello? Hello, Showman?
Whether Sarah,
yeah,
What's happened?
whether
Sir
Sarah
is
left
there?
the platform?
wait. Surajit, most probably, sir has told that
Okay.
he's
Okay.
disconnected. Okay.
Okay. Fine.
Okay, sir, trying to join. If he join, then he can ask.
Yeah. It's not that much of thing. Yeah, we can have our next lecture.
Now come to the second lecture. Actually, this lecture is on differential geometry, and I think the differential geometry is the most important topic for both pure mathematics and applied mathematics. Being a student of applied mathematics and a student of astrophysics, I know that differential geometry is the most important tools to study the celestial mechanics, black hole mechanics, etc., and also the Einstein's metric, Card black hole, Schwarzschild black hole, and in the various field of astrophysics. Now we shall listen to the lecture on differential geometry from Dr. Pradeep Majhi. He is the assistant professor of University of Calcutta in pure mathematics. He has studied MSc from IIT Kanpur and completed his PhD degree and from University of Calcutta. He is guiding at present. He is guiding 4 students for PhD degree, and he has published 50 research papers in different reputed journals. So I am requesting Dr. Pradeep Majhi to deliver your lecture on differential geometry. Please, sir.
Thank you very much for the introduction. Let me first.
Pradeep, the
हाँ,
Sukhendu sir is here. Surajit, now if you want, you can ask question after that.
Yeah, I have just 2 questions. Like as you said, if you have any ternary semi-group, you can embed it inside a mapping kind of ternary semi-group, right? Using that
ternary semi-group mapping.
Y and Y to X, right? Like the Kelly's theorem. So first of all, if what I'm saying, like there's 2 points. Can you just take the all automorphisms, like from X to X, all bijective maps kind of things, and then that information that information gives you the ternary group? If you, instead of taking from all maps from X to Y, you just take all bijective maps from X to X and do the same thing what you did, that will give you a ternary group or not?
So actually, this reduced to a binary operation, and binary groups are always a ternary group.
No, I'm saying you start with so your mapping construction gives you semi-groups, ternary semi-group,
Okay,
not ternary.
I understand your problem. You just you know that if you take the collection of bijective mappings from X to X, then what can I do?
Yes.
I think it is your question. But mind that in that case, if you take the collection of all self maps from X to X, the bijective map, then this forms a binary group.
Yeah, not the
Binary
ternary
groups
group.
are always ternary groups, but ternary group need not be a binary group.
Yeah, and
Fine.
another one question that is very elementary, like in the group theory, you have the Ekman-Hilton duality. Like if you have two binary operations, they are classified like they are same if they satisfy some distributive law, right? If they interdistributed, then they are equal. It's called the Ekman-Hilton duality. So do you have the similar kind of classifications of ternary operations on some fixed object? Like, do you have a Ekman-Hilton duality on the ternary
Actually,
object?
in ternary operations, there is a sister algebra is there. Ternary sister algebra, ternary ring derivation are like that. In that area of research, there are so many equations like you want to do something. In ternary area, there are so many equations in sister algebra, sister ternary algebra, and Jordan ternary derivations.
No, I'm asking something different. I'm saying
Yeah.
if you have two ternary operation,
Yeah.
how can you identify them? How can you classify them? They are equal or not? Is there any way?
Actually, with respect to isomorphic, you can classify this. Otherwise, I don't know another what we can do.
Okay.
One way is the isomorphism property.
Yeah, that is
Yes.
different. That is different. Yeah,
Right.
I'm saying some equational way, like the Ekman-Hilton duality.
Maybe some there are, but I don't know about that equation.
Okay, thank you so much. Okay.
Now I have a proposal to all of our eminent speakers. If they give the copy of their lectures to us, then I can we shall be upgraded in the field of research.
Okay.
Please, and three, I am requesting.
I have already sent my presentation to Sumen.
Okay, sir. Thank you. And I am requesting Dr. Pradeep Maji and Surajit Ghosh.
Okay. I will send you.
I'll send you after my talk.
I will send you to Somen.
Now I am requesting Dr. Pradeep Maji to deliver his lecture on differential geometry field.
Okay, so let me in. Is it visible?
Yes.
Yeah.
Okay, so thank you very much for the introduction. I would like to thank the organizing committee for inviting me to share my thoughts. So I am going to discuss about Gauss-Bonnet theorem. So this is not my research topic actually. So I am working on contact metric manifolds and complex manifolds. But why I choose this topic? Because this topic is connected with topology and as well as geometry. So the Gauss-Bonnet theorem is the most beautiful and powerful, profound result in theory of surfaces. The Gauss-Bonnet theorem combines almost every property of surfaces like curve in R3, especially curve on the surface, Gaussian curvature, first fundamental form, second fundamental form, angles, lengths, areas, geodesic to a single one. Okay. So I am going to present three versions of Gauss-Bonnet theorem here. So the most important version relates the average of the Gaussian curvature to a property of the surface called its Euler number, which is topological, and this Euler number is unchanged by any diffeomorphism of the surface. Such diffeomorphisms will in general change the value of the Gaussian curvature, but the Gauss-Bonnet theorem says that its average over the surface does not change. The real importance of Gauss-Bonnet theorem is a prototype of analogous result which apply in higher dimension situations and which relates geometrical property to the topological one. So before enter into Gauss-Bonnet theorem, let me recall some basic definitions and results for surfaces. So a surface of R3 is a subset of R3 such that for every point P belongs to S, there is an open set U in R2 and open set VW in R3 containing the point P such that U and S intersection V are homomorphic. So please note that S is intersection V is the open set in subspace topology. So this type of homomorphism sigma from U to S intersection V is known as surface patch or parameterization. Collection of all parameterization of the surface patch, a collection of all surface patches whose image cover the whole of S is called the atlases of S. So a surface patch is called regular surface patch if sigma U and sigma V are linearly independent. So note that sigma U is a vector in R3 and sigma V is a vector in R3. So to check this is linearly independent, we need to check only the cross product of sigma U, sigma V non-zero for all UV belongs to U. So a surface patch is called allowable if this is a smooth surface patch and this homomorphism sigma is from U to the open set S. Okay. So a surface is called regular surface if its atlas consists of all allowable surface patches. So a collection of all allowable surface patches is known as the atlases of a smooth surface S. So these are all basic things in surface theory. So I am giving you this example first. So this is a 6 surface patch for the sphere S2. So if we solve this equation x square plus y square plus z square equals to 1 for x in terms of yz, we'll get 2 surface patch, namely sigma x plus minus defined in this way. And if we solve this equation for y, we'll get again another 2 surface patches, and similarly for z, we'll get another another 2 more surface patches. So in this construction, there are 6 surface patches for the sphere, unit sphere, but it can be reduced by using stereographic projection. So by using stereographic projection, one can show that there is only 2 surface patches is sufficient to cover the S2, but not single surface patch is possible to cover S2. Okay, so for the sphere, unit sphere, we have at least 2 surface patches to cover total S2, and in this construction we have 6 surface patches. Okay, so this is another type of surface. Everybody know that this is a hyperboloid of one sheet. This is torus of genus 2. This is helicoid. This is torus of genus 3. So we can extend the genus of the torus. Say torus of genus n. Genus means the number of holes. Okay, here. So here is 3 holes. So torus of genus 3. Okay. So let me recall again a definition. What is called simple closed curve. So a simple closed curve on the surface is defined by gamma t equals to sigma ut vt. So sigma is the surface patch of the surface, say S. Okay. So this sigma is called simple closed curve with period t. If pi t is a map from R to R2. So pi t defined by ut vt is a simple closed curve in R2 with period t. So this pi is a simple closed curve on R2, and this gamma is a simple closed curve on the surface. So this is simple closed or not. It will depends only on this pi is simple closed or not. Okay, such that the region interior of pi. So interior of pi of R2 enclosed by pi is entirely contained in U. For example, this case is allowed, okay, because interior of pi contained in U, totally contained in U, and this case is not allowed because interior of pi is not contained in U, because there is a hole, okay. So the curve gamma is said to be positively oriented if pi is positively oriented. So the property of gamma actually depends on the property of pi, and this pi is on R2, okay. So finally, the image of interior gamma pi under the map sigma is defined to be interior of gamma of gamma. So this is a simple version of Gauss-Bonnet theorem. This is very simple for simple closed curve. So if gamma is a unit speed simple closed curve, unit speed means norm of gamma equals to 1. So there is norm of gamma dot s equals to 1. Unit speed simple closed curve on a surface where sigma of length of gamma, and assume that gamma is a positively oriented, then this equation holds. So what this equation says? Integration 0 to length of gamma kg ds equals to 2 pi minus integration over gamma k dA sigma. So here capital K is the Gaussian curvature of the surface and kg is the geodesic curvature of the curve gamma. Okay, so and dA is the area element of the surface at sigma, and dA is defined by dA sigma is defined by quantity square root Eg minus f square du dv. So Eg, f are all related to the first fundamental form of the surfaces, and the Gaussian curvature is ln minus m square divided by Eg minus f square. This ln minus m square is related to the second fundamental form of surface. So I can give you an example. Suppose we are consider a plane. Surface is a plane. That is S is R2. And we consider the simple closed curve, say circle of radius R. Okay. Then kg and surface of circle of radius R is positively oriented. So the kg will be 1 by R, that is geodesic curvature. Okay. And Gaussian curvature for the plane will be 0. So this term will vanish. Okay. And left hand side will be what? 0 to length of gamma 1 by R ds 2 pi. That is 0 to L gamma ds equals to 2 pi R. That is circumference of the circle. Right. So what this theorem says that if we take any simple closed curve, not necessary circle, any simple closed curve whose geodesic curvature is known to us, then from this equation we can easily get the circumference of this simple closed curve. I mean, okay. So this is a very simple version of Gauss-Bonnet theorem for simple closed curve. Now we'll move to our next version, what is called Gauss-Bonnet theorem for curvilinear polygons. So a curvilinear polygons in R2 is a continuous map pi from R to R2 such that for some real number t and some points t0 to tn, these three conditions holds. So first condition is pi t equals to pi t prime if and only if t minus t prime is integer multiple of pi, and pi is moved on each open interval, and the one-sided derivatives exist and are not zero, not are all zero, and not parallel. If it is parallel, then it will be straight line. Okay, so we are not considering straight line. So the points pi ti is known as vertices of the curvilinear polygons, and the segment corresponding to the open intervals ti minus 1 ti are called its edges. So this is a figure of a curvilinear polygon on a surface. Now we want to know what is the impact of pi, that is curvilinear polygon on R2 on surfaces. So for the surfaces, we have the surface patch sigma, and we have these curvilinear polygons pi from R2, R2. Sorry, there is a typo with R2. And then gamma is nothing but sigma composition phi. So sigma composition phi is pi is curvilinear polygon on the surface. Okay, so this is on the surface and this is on R2. Okay, so interior of gamma in this case will be interior of phi under phi, image of interior of phi under phi, and the vertices will be gamma ti for I equals to 1 to n. Okay, and the edges of gamma are the segments of it corresponding to the open interval ti minus 1 ti. So this is the same notion like pi I for pi is on the plane, and this is gamma is on the surface. Okay, and since gamma is allowable, so this one-sided derivative exists and not parallel. So allowable means this is a smooth. Okay, gamma is smooth from U to R3 function. Okay, so a curvilinear polygon gamma is said to be unit speed if norm of gamma dot equals to 1, and if this gamma unit speed, then the parameter of gamma is denoted by S. Okay, so we have this form, second version of Gauss-Bonnet theorem for curvilinear polygons. So it says that if we consider gamma be a positively oriented unit speed curvilinear polygon with n edges on a surface sigma, and alpha 1, alpha 2, alpha n be the interior angles at its vertices, then this equation holds. Okay, so 0 to L gamma kgds. So kg is again the geodesic curvature of gamma, and this is the sum of the interior angles minus n minus 2 pi minus integration interior of gamma k dA sigma. So dA sigma is the area element and k is the Gaussian curvature. Okay, now we consider three simple cases for this theorem. So first, if we take the curvilinear polygons which A's are geodesic. Okay, so geodesic means the geodesic curvature, that is kg will be 0. So we are considering here any curvilinear polygon, and here we are considering the curvilinear polygons whose edge is geodesic. So edge geodesic means kg 0. So kg equals to 0 means this part will vanish. Okay, so only remaining part will be this. Okay, so this is a corollary for a curvilinear coordinates with n edges, each of which is an arc of a geodesic. Then the interior angle alpha 1, alpha 2, alpha n of the polygon satisfies the equation this. So this is very easy, and it follows from curvilinear Gauss-Bonnet theorem for curvilinear polygons. Okay, so this is immediate as kg equals to 0. Now, if we consider n-gon on a plane, so see geodesic of the plane or straight line. Okay, so we are considering the surface is plane and n-gons. Okay, so the edges are straight lines. Okay, so the geodesic curvature of plane is k equals to 0 for the plane, and this corollary says, so this is 0. So this corollary says sum of the interior angle, okay, alpha 1, alpha 2, alpha n equals to n minus 2 pi. So this is very well known formula in elementary differential geometry. Okay, so if we consider n equals to 3, then sum of the interior angle of a triangle is pi. This result recovered, right? So this is a very preliminary results. We know it from our school level, right? So it can be generalized by using Gauss-Bonnet theorem. So Gauss-Bonnet theorem generalize all those things. Okay. So the second case is if we consider n-gon on S2. S2 is a unit sphere. See, S2 the geodesic in this case are great circles, right? So for S2, if we consider n-gon whose geodesics are great circles, And for S2, we have the Gaussian curvature k equals to 1. So this summation of interior angle exceeds the plane value n minus 2 pi by the area this, right? So we have the k equals to 1 here. So this value is exceed the plane value n minus 2 pi by this area. Okay. So if we take n equals to 3, we get the area of the spherical triangle with angles alpha, beta, gamma, whose edges are the arc of the gate circles. So in this case, area of the circle will be alpha plus beta plus gamma equals to minus pi. See this picture. So this is a triangle. So this is a triangle on a unit sphere. So area of this triangle is alpha plus beta plus gamma minus pi. So we can generalize this concept if we in any curvilinear polygons on S2, not necessarily n equals to 3. Now we consider another case. So for pseudosphere, if we take the surface is pseudosphere, and if we take n gons, for the pseudosphere case, the Gaussian curvature is -1. So then sum of the angles is less than n minus 2 pi by the area of the polygon. So in this case, area of the polygon n minus 2 pi minus alpha 1 minus alpha 2 up to minus alpha n. So if we take n equals to 3, then the area of a triangle on a pseudosphere is pi minus angle of A minus angle of B minus angle of C. Okay. Now we will go to our next version, what is called Gauss-Bonnet theorem for compact surfaces. So this theorem, this version of Gauss-Bonnet theorem we are aiming for is obtained by covering a compact surface S with curvilinear polygons. So to be precise, we begin with the following definition of triangulation. So let S be a surface with atlas consisting of the surface patches sigma I. So a triangulation of S is a collection of curvilinear polygons, each of which is contained together with its interior in one of the sigma ui, such that every point of S is at least one of the curvilinear polygons. Second condition, two curvilinear polygons are either disjoint or their intersection is a common edge or a common vertex, and each edge is a edge of exactly two polygons. Okay. For example, this kind of figure is not allowed. Okay. Since we have this second condition, that is two curvilinear polygons are disjoint or their intersection is a common edge and common vertex. So here is no common edge and common vertex, right? So this kind of case is not allowed. So for example, if we take a sphere, so the triangulation of sphere S2 unit sphere with 8 polygons is obtained by intersecting with the 3 coordinate planes. So this is a polygon. This is a polygon for upper hemisphere part. There are 4 polygons, and for lower hemisphere part there are again 4 polygons. So there is 8 polygons, right? So again, we know that a very important result that every compact surface has triangulation with finitely many polygons. So we introduce the following number associated to the any triangulation, what is called Euler number. So the Euler number chi of a triangulation of a compact surface S with finitely many polygons is defined by in this way, that is chi equals to V minus E plus F, where V is the total number of vertices of triangulation, E is the total number of edges of the triangulation, and F is total number of polygons of the triangulation. So for example, if we take this triangulation for the sphere, so in this case vertices, number of vertices is 6, number of edges is 12, and number of polygons is 8. So the Euler number is 6 minus 12 plus 8 equals to 2. So for S2, that is unit sphere, the Euler number is 2. Now, the most important of the Euler number is that, so this Euler number is unchanged by any triangulation, but it depends only on the surface. For example, if we can get another triangulation for S2 by inflating a regular tetrahedron, if we take this triangulation for the sphere, so in this case, number of vertices is 4, number of edges is 6, and number of faces is 4, right? So in this case, the Euler number is again 2. So the Euler number is actually depends on the surface only, but not on triangulation. Okay. So this property of the Euler number is consequence of the following theorem, what is called Gauss-Bonnet theorem for compact surfaces. So if S is a compact surface, then for any triangulation S, so integration over k dA S k dA equals to 2 pi x. So this is for any triangulation S, right? So from this result, we can easily say that the Euler number chi is independent of triangulation, right? So this is independent triangulation, left hand side. So this is also independent of triangulation. So Euler number is independent of triangulation. And see, this is left hand side is only geometric properties are there, and the right hand side is the topological property. That is Euler number is topological property, and this is a totally geometric property. So Gauss-Bonnet theorem for compact surfaces can a bridge between you can say bridge between topology and a differential geometry. Okay, so to see, this is why this is a remarkable theorem. So let us apply it to S2. So for S2, Euler characteristic is 2, right? So chi is 2, Euler number or Euler characteristic is 2. So we get integration S2 k ds equals to 4 pi. Okay, so this is not so remarkable because for S2 we know k equals to 1. So this is just area of S2, right? But if we deform S2, so we think S2 as being a rubber sheet, and we pull and stress in a way we like, but without tearing and producing a new surface S. So this is a new surface. We deform it from S2, right? So from this surface, for this surface, the Gaussian curvature is not k equals to 1, right? So Gaussian curvature for S2 is 1. This is constant, but Gaussian curvature for this surface is not 1. Okay, so to calculate this k dA part will be very difficult, right? But by using the Gauss-Bonnet theorem, how do you use Gauss-Bonnet theorem? So if we start a triangulation of S2, then after deformation, we shall have a triangulation of S with the same number of vertices, edges and polygons as the original triangulation. So after deformation, the Euler number for this surface will be 2, right? So it follows that from the Gauss-Bonnet theorem of compact surfaces, the k dA equals to again 4 pi. So this is the volume of the surface S. Okay. So more generally, this discussion shows that any two deformatic surface, compact surface, have the same Euler number. Now we complete our picture by determining the Euler number of all compact surfaces. Why all compact surfaces? Because we know that a compact smooth surface is diffeomorphic to Tg. Tg is torus of genus 2, where G is greater equals to 0 and G is any non-negative integer. Okay, so if we prove this theorem, then we complete our picture by determining Euler number of all compact surfaces, because any compact surface is diffeomorphic to Tg for some G, where G greater equals to 0 and an integer. So the formula is correct when G equals to 0. So G equals to 0 means genus 0. So this is a S2 itself. Tg equals to S2, that is hemisphere. Since we have chi equals to 2, a sphere, already we know that g equals to 0, the result is true. Okay. Now we will prove the result for T1, that is torus of genus 2, 1. Okay. To find a triangulation of the torus, we use the fact that it can be obtained from a square in a plane by gluing opposite edges. So this is a square on a plane. So we first glue it, it will be like cylinder, and then we glue again, it will be a torus. Okay. So we start triangulation of the square. So we subdivide the square into triangles as shown. So you can subdivide the square into triangles in this way. So this leaves the triangulation of T1 with V equals to 9. Why V equals to 9? So one must count carefully, because these 4 circle vertices is a single vertices on a torus. Okay, so if we glue this way, these four circle vertices is a single vertices of torus. So in this case, V equals to 9, E equals to 27, and F equals to 18. So note that not just any subdivision of square into triangles is acceptable. For example, if we consider this subdivision, so this subdivision is not acceptable for square, because after gluing, 2 shaded triangles intersect into 2 vertices, okay, which is not allowed according to the definition of triangulation. So if we consider our earlier version, that is this version, we'll get the Euler characteristic chi equals to 9 minus 27 plus 18, that is 0. So you can write in this way 2 minus 2 into 1. That is, we prove this theorem for g equals to 1. Actually, we want to prove this theorem by induction. So we now complete the proof of by induction on g. So using the fact that Tg plus 1 can be obtained from Tg by gluing on a copy of T1. So this is Tg and this is T1. We want to glue this. Okay. So how do you glue this? We just remove n-gons from this Tg and n-gons from this T1. So we'll get the number of vertices. So V prime, E prime, F prime are the number of vertices for Tg, and V double prime, E double prime, F prime are number of vertices, edges, and polygons for T1. So in this case, if V, E, and F for Tg plus 1, then we will get V equals to 1. V equals to V prime minus N, V double prime minus N plus N, ultimately V prime plus V double prime minus N. Indeed, V is the number, V prime of the vertices in Tg plus V double prime vertices in T1, except the n vertices of the polygons along T1 and Tg are glued, have been counted. Okay, the similar way we'll get capital E and capital F. So a similar argument applies for the edges and faces, already I have said. So in this case, we can calculate the Euler number for Tg plus 1, that is torus of genus G plus 1. So it will be what? V minus E plus F, and we substitute the value, previous value, we'll get ultimately 2 minus 2 plus G plus 1. 2 minus 2 into G plus 1. So proving the result for genus G plus 1. So what can I say from there? So this result, so this result is true, right? So this result will true by induction. Okay, that is the Euler number for compact surface Tg of genus G is 2 into 2G. Okay. Okay. Now, by using Gauss-Bonnet theorem of a compact surface and the previous theorem for the torus of genus G, we can conclude this result, that is integration over Tg k dA 4 pi 1 minus G. So application of this result is follows. If we take any compact surface diffeomorphic to a torus G1, So torus G1, T1 means genus 1. G equals to 1 here. So right hand side will be 0, right? So in this case, integration over S K dA equals to 0. That is, for any compact surface S which is diffeomorphic to a torus T1, this integration will be 0. Okay. Now, suppose that S is a compact surface whose Gaussian curvature is strictly positive. Okay. Strictly positive. So Gaussian curvature strictly positive means what? This integration is strictly positive. Okay. So this integration strictly positive means what? 1 minus g is strictly greater than 0. That is g is strictly less than 1. So g is greater equals to 0 and integer. Okay. That is g is a non-negative integer. So g must be 0. Right. So S is diffeomorphic to a sphere. So any compact surface whose Gaussian curvature is strictly positive everywhere, diffeomorphic to a sphere. So such kind of result can be easily followed from the Gauss-Bonnet theorem of compact surfaces. Okay. Now we'll generalize this Gauss-Bonnet theorem on manifolds. So let me recall few things about manifolds. So in manifolds, smooth function on Euclidean spaces. Smooth function on Euclidean spaces, everybody will understand, I hope. So this is a smooth functions on Euclidean spaces. So smooth manifold is a housed up and second countable topological space. So a coordinate chart or just a chart of M is a pair Ux, where U is an open subset of M and X is U to Rn is a map such that Xu is a open subset of Rn and X is a homomorphism from U to Xu. Then these two charts, this first condition is known as locally Euclidean. Okay, so M is locally Euclidean. So locally Euclidean means this type of condition should satisfy. Okay. Now, if we take two charts Ux and Vy, where U intersection V is not phi, then the transition map X composition Y inverse. Picture is this. This transition map is a diffeomorphism. Okay, this is the second condition. See, this is Rn. This is our manifold M. This is X from U to Rn. This is Y from M to Rn. So this is our transition map X composition Y inverse. So it is from X U intersection V to Y U intersection V. So the third condition is the collection of all charts Ui Xi is atlas on M if any two charts are computable and intersection Ui equals to M. Okay. Two atlases are equivalent. We say two atlases are equivalent if atlas A1 script A1 union script A2 is again an atlas. So a differential manifold is a topological space with symmetry structure, or on a M is a equivalent class of atlases. So a smooth manifold of dimension is a topological manifold together with the differential structure. Okay. Now we'll state the Gauss-Bonnet theorem on a even dimensional hypersurface in R+1. So if X is compact even dimensional hypersurface in Rn+1, then integration over K, that is Gaussian curvature of this surface, is half of gamma n into chi x. Chi x is Euler characteristic or Euler number of X, and gamma n is the volume of the unit n sphere. Okay. So in this way, we can generalize the Gauss-Bonnet theorem. So there are many more generalization of Gauss-Bonnet theorem in higher dimensions. So I am not going to show all those things. So I am taking these materials from the book of very elementary book of differential geometry named elementary differential geometry by Presley, and differential topology by Bulliman and Plork. If you want an interest, you can see those books. There are many such results. So I want to stop here. So thank you very much. Thank you for your attention.
Now we shall come to the interaction session. If there are any question to Professor Odit,
Yes, I have one question. Yes, I have one question.
Most welcome, Surajit.
Yeah, the question is the definition of Gauss-Bonnet theorem says if you take the integration of the Gauss curvature on the manifold, that will equal to the 2 pi of or some constant of the Euler characteristic, right?
Yes, yes.
Now the point is, assume that we know from the Miller's result that in the 7th dimensional sphere, they have 7 different differential structure, but both are homomorphic. All are homomorphic.
Okay.
So, right now, your right-hand side of the Gauss-Bonnet theorem says this is a topological property because it doesn't change under homeomorphism. So that means whenever you put any kind of 7 spheres, which created by Miller, your right-hand side will always be same, right? Because it depends on only topology, not on the differentiability. But since it has this 7 different differentiable structure on the 7th sphere, so the left-hand side should depends on the differentiable structure, right? It's a geometric structure. So it should change. So what is the gap here, right? One side is not changing because the homeomorphism preserving property, one side is changing because of the 7 differentiable different structure. So that is something confusing for me.
So in my opinion, the left-hand side is the average of the Gaussian curvature, right? So perhaps this.
No, that I understand. But if you fixed one manifold with a certain differentiable structure, that will give you some fixed value on your left-hand side. If you change your differentiable structure on the manifold, that will give something else, right? Okay. Or maybe the Gaussian curvature is not changing on the differentiable structure.
Okay.
That I don't know. That I am asking. If you change the differentiable structure on a manifold, is under certain condition, like if you have a manifold M, so one differential structure is D1, and if you put another differentiable structure which is not equal to that is D2, and you have 2 different manifold, right? But the underlying manifold is same, they are M, but with different kind of structure. So how the left hand side of the theorem is changing or not changing, that I really don't know.
Actually, I don't know actually really it's, but I don't have idea, Surajit.
Or maybe it's not depending on the differentiable structure. Maybe. Yeah.
Maybe it cannot be happening.
I don't know.
I don't know about, but I think this.
What Sukendra say?
Actually, I don't know what about that, but what Surajit said, I think the both sides are some sense they have some equality, but how can I
I understand that your left hand side is not depends on the differentiable structure, it depends on the only triangulation. Yeah. So maybe different differentiable structure gives you the same triangulation. Yeah, maybe. Yeah.
I have shown an example of a surface and deform it. See, S2 is a surface of Gaussian curvature 1, right? So if we deform
the surface, that is not true, Pradipta. That is not true. You can't deform anything. So you have to say what is the meaning of deformation in your language. But deforming in general means like if you take a disk, you can deform it to a point, right? Right.
No,
deformation means a continuous deformation from one object to another object by a continuous map. So the deformation, if you take this kind of deformation, continuous deformation, that will gives you something else. That don't preserve the Gauss-Bonnet theorem. You have to say deformation under the diffeomorphism, not under the homeomorphism. So it's some kind of special diffeomorphism. Otherwise, it's not valid. Otherwise, it's not valid.
No, that is also that I have already told you. Na, this is deformation is a diffeomorphism only.
Okay.
First, I told you. Okay.
Okay. Fine. And another one question. It's a little. It's based on the definition. Whenever you say manifold, you don't need the maximal atlas.
Yes, maximal is needed.
You always need the maximal atlas, right?
Yes,
Whenever you say them.
yes.
Okay.
Yes.
Yeah. I think it was missing in the slide. That's why I'm asking.
Okay. Perhaps the A1 union A2 is for maximal atlas. Perhaps I missed those slides.
Yes. Yeah. Anyway, fine. Thank you.
Okay.
I have a question to Dr. Pradeep Majhi.
Yes, please.
Hello. Is Gauss-Bonnet theorem applicable for the virtual surface like light cone we use in the astrophysics on black hole theory?
No, the surface should be compact, right? So I don't know the virtual surface light cone compact or not.
Okay.
The restriction is surface should be compact.
Yeah.
Thank you.
Yes. So I think that's why it's not a hyperbolic thing, right? Do you have anything in the hyperbolic manifolds? Anything? Gauss-Bonnet theorems? Like any trees? If you have any compact trees, graphs. So they always have a hyperbolic group structure, a hyperbolic structure, right? You can talk about the negative curvature. So do you have any? It's not. I think it's not valid in the hyperbolic case. Maybe I don't know. Yeah.
I don't know also the Gauss-Bonnet theorem whether valid or hyperbolic.
Yeah. Okay. Fine.
Thank you.
Okay, thank you.
Thank you, Dr. Pradeep Majhi, for delivering his important and interesting speech on differential geometry and manifolds. Now, our last and third speaker is Dr. Surojit Ghosh.
Yeah.
His lecture is on the topic topology. Topology is most modern concept in mathematics. Dr. Ghosh has completed MSc degree from IIT Kanpur and awarded PhD degree from Ramakrishna Mission Vivekananda University, Belur. He has published many research papers in reputed journals. Now he is connected in research work at postdoctorate level in the University of Haifa in Israel. I am requesting Dr. Surojit Ghosh to deliver his lecture on the topic of topology.
Yeah, thank you so much for the invitation and thank you for having me. So today I'll talk about something called topological Trademark conjecture, which is something related to the combinatorics or rather topological combinatorics data. What is it is all about? It's all about the partitioning of points inside a plane. Okay, so if you fix some plane and put some points which are in the generic position, generic positions mean they form a simplex, in that bigger dimension. So like it's not like collinearity, it's not like coplanarity. It's like if you take 3 points, it should be form a triangle, not in the same line. If you take 4 points, it should be gives you a tetrahedron in R3. This kind of position is called the generic positions of the points in the Euclidean space. So if you start with a Euclidean plane and put some points inside it, specify some points inside it, then you can ask, can you partition these points in certain ways such that the intersection of the convex hull of that guys should be non-empty. So that means they should be convex. The convex hull should be dense inside. So this conjecture is a very old conjecture. It's 1966, and today I'll talk about this conjecture and I'll explain how you can relate this totally combinatorial thing with the equivalent homotopy theory purpose. Okay. So let's start with what is this conjecture all about. So the conjecture is, before going to the conjecture, I'll say some few words about the convexity and the convex hull, all the basic definitions from the basic geometry. That's the convex is like, if you choose any 2 points, you can join the line should be inside the space. Okay, and a convex hull, it's depend on some set. If you choose some set inside Euclidean space, you take the minimal convex set out of it, and that's called the convex hull. And we denote this kind of convex hull for certain set as a conv x, like this. Okay, now you have, now I'll explain what the statement for the conjecture. The statement is, if you take any set with d plus 1 into r minus 1 plus 1 points in RD, and whenever I say points, the points are in the generic position. Okay, they are in the general position. They are the generic points. They're not inside one line. They're forming a this minus 1 dimensional simplex. Okay, so that is called the generic position point. And whenever you have this number of points, you always have certain partition, and the number of partition depends on this R. So you have the R number of partition of the set A, and then you take the convex hull of all the subsets AIs and take the intersection, that will give you the non-empty set. Okay, so this is the statement of the conjecture, and I'll try to understand this conjecture in a continuous way. So now this conjecture is very discrete. You have some certain discrete point, you make them discrete partition, and you just talk about the convex hull. So it's a very discrete view of the conjecture. So yeah, later I'll try to understand as a continuous generalization of this conjecture. So okay, before that, just a small warning. Whenever the number of points is less than equal to this ultimate number, you have nothing about this kind of result. So the conjecture will be false. So we can see some pictures to understand this situation. Like if you take usual case like Euclidean plane, d equal to your d equal to 2 and r equal to 3. So let's start with this case, d equal to 2 and r equal to 3. So this big number is equal to 7. So you are, I said you have to choose 7 points in such a way that the convex hull of the 3 kind of partition should have a common point. So I have these 7 points, these blue points, and I have partitioned this in 3 kind of sets, like 1A, B, C, and E, F, and another partition is D, G. Okay, so you have this 3 partition, and whenever you take the convex hull, that will generate that dimensional simplex, and the first 3 points gives you a triangle, and the second 2 partition gives you 2 lines, and you can understand they have a common intersection points. So that means the conjecture works very well here if you have this smaller dimension case. Also in the we can see that if this big number is the optimal number for the conjecture, if you make one small of this number, then that will destroy the all statement of the conjecture. So let's take this. Here you have the same situations, but you are taking one less point. So you will only have 6 points. You cannot partition this 6 point into 3 groups so that the convex hull is non-empty. It's not possible. This is a prototype case for the partition of this set of 6 points, and you take, this is one prototype. You can do the similar thing by rotating these triangles everywhere, and you can understand it's not possible, because you have this triangle is the first convex hull, and the second convex hull of 2 points is this one. But whenever you do those things, you always left off a point, right? So it's certainly not possible to do this kind of situation for 6 points. So okay, so I will try to restate this conjecture in a more mathematical, or rather more topological way, or more linear or affine algebraic way. Okay, so let's start with the definition. What is the meaning of a simplex? So simplex is a very canonical object to, it is a model. It is a model for the disk inside a Euclidean space. And if you take the boundary of a simplex, it will gives you a model for the certain spheres. Okay, so as you see in the last talk, Pradipta was talking about the Euler characteristic and the Gauss-Bonnet theorem. These things, whenever you said this kind of things, you have to do some triangulation, and whenever you do triangulation, you have to do the integration over all paths on the triangulation. Then you will get some result which connects to the Euler characteristic and all those things. But what is the specific triangulation of sphere? Like whenever you take a sphere, you have seen like a sphere has a triangulation with 4 points, 6 edge, and 4 face. So this is the right guy for the triangulation for the sphere. If you take the boundary of this guy, only the faces, not the not the filling. You just remove the filling of it. What you get, it's called the triangulation for sphere. And in topology, everything what we understand, everything is coming from either sphere or a disk, and you have to attach the spheres to the disk or something else under some continuous map, and you'll get any kind of object in topology. So basic objects are disk and spheres, and we understand the triangulations for this disk is this delta n, and the triangulations for sphere is the boundary of delta n. So this simplex is a very important object to understand the topological, rather the homological or homotopical properties, not homotopical, rather the homological properties of the topological space. So this is a primary object to study in algebraic topology. Okay, so now we just talk about the restatement of the conjecture. So we have seen we take d plus 1 into r minus 1 plus 1 points in Euclidean space, and you want to understand this kind of situation in more topological way. So points are discrete, so topology is discrete, so we don't bother about this kind of situation. It's very combinatorial aspects, but we just move on to using the generic positions or general positions of the points. And whenever you have a certain points in general position, that gives you a simplex like this. So the restatement should be this kind of thing, like you fix some integer d and fix some number r, which gives you the number of partition, and fix the number big N is the n plus 1 into r minus 1. Then the restatement of the previous conjecture is said for any affine map. So affine map means it is a linear map up to some constant. So it is like ax plus b. So if you have any affine map, then you always have r disjoint face. So what is a face? It is it's already described by Pradipta in his slides about triangulation. So face are the building blocks of the simplex of or triangulations. Okay, so if you have any face, they are maybe in different dimension. They could be in a dimension 1 to dimension of the simplex n. And if you have any affine map, you can always make a partition of the this simplex delta n into r copies, such that the intersection under this map inside this Euclidean space have a non-empty intersection. Okay, so that means they always share a common point. For example, I can tell you a very basic example. If your d equal to 1, what happens? If your d equal to 1, you have 2 into r minus 1 points. That means even number simplex. That means you have odd number of points. So whenever you have an odd number of points, you just take so your image is going inside the one-dimensional Euclidean thing, that is only r. So you have r, and on the r you have r distinct point. So you take the least value and the highest value and define it as an interval, and that is the convex hull. You take the second least and second highest and do the similar thing, and the last one is a single point. Then you do the convex hull and take the intersection. What you get, it's just a single, the least partition, the single point inside the smallest partition, that one. So it is always non-empty. So for d equal to 1, it's very easy to understand the Trademark conjecture is true. Okay, fine. Yeah. Now the conjecture is, so this theorem, it's much more linear algebraic theorem. It's all about the convex geometry. It's not, no topology is related here once you say the affine map, because you are very restricted to doing these things. Your maps are very special. So now the real question is, when you change this affinity of the map by a continuity. So the question is, you have the same situation, you change your affineness by a continuous map, then what will going to happen? Is the conjecture is true or conjecture is false? That is the main question for like last 70-80 years. So now I'll tell you something about how to understand this question using more equivariant homotopy theory. So this conjecture is called topological Trademark conjecture, and we just say who are the players of this game, who will change this game using their efficient effort. So first of all, our group will, if you say equivariant homotopy theory, that means you have to fix some group. So our group is always a fixed finite group. Fine, throughout the talk, the group will stand for a finite group. Second, what is the meaning of the G space? You just take a topological space with a continuous G action. Why this continuity matters? Because whenever we study G action, it doesn't mean it should be continuous or not, but we are specific about this thing because we have to talk about the mapping objects. As from the first talk, we see there is something called mapping object. So the mapping object should be like from maps from X to Y, that should have a compact open topology, and that should have an action of the group G by conjugation. So that kind of objects are very important in our study. So yeah, so this is called the G space, and yeah, and a map is called a G map if it respects the action. So you have a 2G space X and Y, and it comes with two action by the same group G. Then we can talk about the equivariant maps between them, or sometimes we call G maps. If it respect the G action like this, it cannot eat the group. It will always take away the group. Okay, this is the meaning of the respecting the action. Fine. So another definition which is playing a main role in studying this kind of things is called the H fixed point. We all know these things, but yeah, just for recollectment of the all known data. So fixed point is something which is not moving under the action. So whenever you have a fixed point, it's not moving under the action. Okay. So the action is trivial on that part. That is the definition of fixed point. Okay. So fact is, whenever we talk about the fixed point, we understand that it's not moving under the action of H. That means you have something where the group is acting, but the subgroup H acting trivially, right? That means it equipped an action of the while group of that subgroup H. What is the while group? It's the normalizer quotiented by the subgroup H. Fine. So it always comes with this action freely. Not free action, it comes free. So I'll talk about the more players who will play the roles. So it's called the GCW complex. It has a very complicated definition, but I try to make it as simple as possible. So a GCW complex is a G space. That means it has a G action and it has a filtration. So once it has a filtration, that means we try to understand that it should be constructed inductively via the attaching cells. We call this kind of things as cells. It's what is this? This guy is a disk in the Euclidean space of dimension k. And what is this one? This is just, you can think like it is a G mod H copies of D. Okay, so you have a disk. You take the G mod H is a number, the cardinality of G mod H. You take G mod H copies of dk, and one guy is going to another guy given by the G action. So it's kind of now fixed, it kind of finite number of disks and moving each other. So one guy is going to another guy is going to another guy. It's some rotating finite number of disks. Okay, so this is the building blocks for this kind of complex. It is some kind of generalizations of GCW complex, or rather I can tell you this is as you have seen in Pradeep Das talk, that it is some kind of related to the triangulation. We have seen a triangulation is something where you are playing with the triangles, right? You want to fill some manifold using or surface using triangles, and here we are filling manifolds or surface or in general topological space by disk. So you just change triangles by disk, and what you get, it's called a CW complex. And here we have a more structure. It's called the GCW complex because here our disk comes with an G action. It's not a trivial. So if your G is equal to trivial and your disk equal to triangle, what you get is called the triangulation. Okay. So yeah, so what are the basic example for this? So if your V is a G orthogonal representation, what does it mean? A orthogonal representation or a representation is nothing but a vector space comes with an action. So once you have a vector space, you can so always we have, if you have a vector space, you can fix the number of bases. Once you fix the number of bases, then always we have an action of the orthogonal group, right? Then orthogonal groups rotate the basis by the rotation, and what you get, it's called the action of the orthogonal group. So always a groups comes with an, always a vector space comes with an action of orthogonal group. So one can understand the all automorphisms from V, the vector space V, the linear automorphism, as a orthogonal group of dimension of V. Okay, so we denote this kind of situation by OV. So it is all linear automorphism from V to V. Okay, so a representation is a G action over vector space, and once you have G action over vector space,
I think
yes,
I think you have to take the orthogonal, means you have to take inner product space.
yeah, that I'll tell you in a minute. Just a minute, I'll tell you in a minute. Yeah, so that is the point. So what is the meaning of the inner product, all these things? Okay, so yeah, our vector space comes with an inner product, that's fine, but that is not the whole story. So the whole story is, you have, if you have inner product, why it respect the G action. So we know if you have an inner product, we can apply element G. So you have a x comma y, you apply gx comma gy. So we know gx comma gy may not be equal to x comma y, right? So we not only we have the inner product space, we also need a G invariant metric or inner product on it, right? So that's the, but you know, whenever you fix the orthogonality, we can do the averaging business. We can average the usual inner product structure by the number of elements in group G. Like you can do the summation gx comma gy and mod out by the order of G, and you have, what you have is something G invariant inner product on the vector space V. Okay, so you not only need the inner product structure, and also you need the G invariant inner product structure, okay, to define the orthogonal representations for a group G. So that I said in a minute, that I told you. So your G invariant norms is given by the averaging over G. So now when you have a G invariant norm, we can talk about the disk inside the vector space. You can talk about the spheres inside the vector space, like in the usual Euclidean space. So what is a disk? Disk is all the elements where norm is less than equal to 1, and sphere where the norms are equal to 1, and this plays as a role of boundary of the disk. Okay. Now we can talk about the one-point compactification of the vector space, because it comes with a topology, so we can do the compactification. So once you do the compactification, or rather you can do the quotient topology from here to here, like you quotiented the disk dv by the sphere sv, what you get, it's called the one-point compactification of the representation V. So yeah, So this is one this is one explanation for the one-point compactification. Like you start with real numbers or Euclidean plane R2, and you take the all vectors that which norms less than equal to 1, that is disk, and you just quotient by the boundary. That means you taking all the boundary to a point, that's give you a sphere S2 inside R3, right? So same thing is going on, but here the point is, here everything comes with an action. So it has an action which induced from the action of the orthogonal representation V. Okay, so these are some examples of CW complex, and now I'll talk about what is the deformation that Pradeep just said a few minutes back. So what is the meaning of the deformation, and how you can understand all this Trademark conjecture under this deformation business. So let's start with the definition called the equivalent homotopy. So what is the homotopy is? So I'll tell you it's equivalent analog of the usual classical homotopy, but the point is you can do the same thing for any finite group action or also any compactly group action. It's not that much hard. So I'll tell you something called the G homotopy. So what does it study? So we usually use the homotopy theory to study the G spaces. That space comes with an action, and also we study the G maps. That means that continuous map which respect the action. And we study these two objects. We have to study these two objects under some certain relation, and that relation is called the homotopy. So what is that? This is a continuous deformation from one map to another map. Okay. So this is all about the point of studying equivalent homotopy theory. And once you have two maps, F and G, which are the G maps in our sense, then we say the G homotopy is a continuous G map. So whenever I miss continuity, you should assume that everything is continuous in this business. Everything is. So whenever so you have a G map which is from the cylinder to the space Y, and it's deformed one map to another map. So rather we should see one picture, like you have a map F and G from the top part and from the bottom part, and this is one cylinder over your X, and you can press this top of the cylinder to reach from X cross 0 to X cross 1. That means you have a continuous deformation from the map F to map G. So this is the whole point of the homotopy. So the fact is, whenever you have this kind of homotopy, this defines a relation, and this relation is an equivalence relation. That's the main point of this kind of picture. So once you have a relation which is equivalence relation on the set of maps, then you can make the you can quotient it by the relation. What you get the like homotopy equivalence classes, and we denote it by the bracket X comma G, and we also mentioned this G to, we don't want to forget the action of G. So this is will remind you what are your group is, what is your group. Okay, so this is the state of equivalence, and we call one map like this bracket F, and under this relation homotopy relation. And fine, and if your G is a trivial group, then we call it is a classical homotopy or usual homotopy, and we denote this thing by X comma Y only. We forget about G, where your G is a trivial group. So this is all our players. And then I just want to talk about something. Whenever you have a notion of homotopy, we should have what is the meaning of the homotopy groups. So homotopy groups is something whenever you put your X, you substitute X by a sphere in some dimension, like you take the sphere, k-dimensional sphere, and the topology comes from the Euclidean space topology, which is given by the subspace topology. And once you define this, you have a natural action over it. So what is the natural action? So the natural action, I'll give you the picture. You start, for example, if your k equal to 1, you can do these things for any k. So whenever your k equal to 1, you have this circle, and just take two antipodal points of the circle and try to pinch them off. So if you pinch them off, you get two circle pinching at a point. It shares only one common point, and on the top of the point you define your map F to Y, and on the bottom of the point you define your map G. So whenever you have such a diagram, you just try to do the composition of this whole picture. What you get, it's some operation, it's a group operation, it's some binary operation, not trinary. So yeah, it's a binary operation, and this under this operation you can what you can do, you can have a group structure, and it has the inverse, because homotopy comes with an equivalence relation. It comes with an inverse operation by what should be the inverse of this, some f. The inverse is like rotating from in opposite direction of the circle. It gives you the inverse. It's like some path business. If you have a path from certain in certain topological space, you can write path as a map from interval to the topological space X, gamma t, and if you put gamma 1 minus t, that will give you the same path with reverse order, right? So you have the similar notion here on the circles also, because circles are nothing but a path identified the n vertices. Like if you have interval, you identify 0, 1, you will get a circle. So you have the similar kind of notation. So you can define the inverse of the map. So this guy Phi1y is called the fundamental group of a topological space Y. And whenever you do these things for general K, you have for general sphere also, you can do the pinch business and define the same thing. You will get a group structure. On the higher homotopy groups, it's called higher homotopy groups. And the main point of the whole story is, if your sphere has dimension more than 2, okay, then these groups are abelian groups. That we can understand very frequently, because you can have enough space to move around, right? If you have two map, you can move one to another, because you are in R2. Just think like R2, okay? In R2, if I specify 2 points, you can move around. You can make them. You have enough space to move one points to other and another points to the previous one. But once you are in R in real line, you have 2 points. You can't cross one by other, because you have to hit each other. So if you fix 2 points in R and you trying to move one point to another point's direction, at some point to cross the point you have to hit that point. So that means you don't have enough space in R, but once you are in higher Euclidean space, you can have a lot of space. So you start with two map F and G that gives you value fx and gx. You can move fx and gx to gx fx. So that means they always have a abelian structure. So for k bigger than equal to 2, these groups are abelian groups, and that is a very crucial point to understand the homotopy groups. It gives you some other direction called the stable world. That's different. Okay, fine. Now I try to do. I just explained something called the homotopy groups. Now I try to explain something called the homology groups. And as you know, in the last talk, we see the Euler characteristics. So Euler characteristic is something which is invariant under homology. So here we can do the similar kind of things. And before doing the homology, we have to say something. What is the coefficient system of the homology? So let's. So in general, in the usual classical homology theory, we use any abelian groups or any Z module as a coefficient. But here pictures are different, because here everything comes with an action. So we define in rather categorical way. So we define the orbit category OG. So OG is a orbit category. So once you have an orbit category, it should have some objects and some morphisms. So it comes with an objects as orbit G mod H, where H is a subgroup of G, and also it has some morphism. Morphism given by the G map that I explained in my first slide. So now I can ask you one question, that whenever you have a G map between two G orbit like F, it only exists, this kind of G map, if and only if there exists an element G inside G such that H is subconjugate to K. So this is a very important property to study the fixed points. Okay, so this is some aside. It's some exercise to understand the G business inside this orbit category. So once you have the orbit category, we can define the coefficient system. So what is that? A coefficient system is a contravariant functor from the orbit category to the category of abelian groups. Okay, so what does it mean by functor? Functor means it will assign the object to some object here. It will assign some map from here to here, and also it will respect the composition. So once you have a composition of two map, it will respect that. And once you have an identity map, it will respect the identity also. That means it will send identity to identity. Fine. So these four property will go together, assemble, and gives you a gadget called the functor. And what is the meaning of contravariant functor? Contravariant means whenever you have a category, you just forget about everything. You take the object and see from your other side. Means you just see the maps from a different direction. Like all the maps are in a reverse direction. Okay, if you have a map like G mod H to G mod K in the opposite category or as a contravariant functor, it will send this guy to something from G mod K to G mod H. It reverses the orientation. Okay. So this is called the contravariant functor, and once you have this thing, we can define the coefficient system as a contravariant functor from the orbit category to abelian groups, and then we can see one example coming from the homotopy. Okay, so we have seen that if n equal to k or k n equal to 2, we have seen the homotopy groups are abelian. So because we are landing here in the abelian groups, that means this is the more reasonable place to work with. So we always work for n bigger than equal to 2, and we talk about the abelian homotopy groups. So now we defined a coefficient system. So I told you that whenever you have a coefficient system, it is a contravariant functor. That means it will eat one object which is an orbit, and it gives some abelian groups. So here it eat the object G mod H and gives the homotopy groups of fixed points. And as we have seen, n bigger than 2, it's an abelian group. That means it satisfies the above condition. And you have to work out for the maps how it behaves on the morphisms like F. But this observations gives you how it behaves. It's not that much hard, so it's left as an exercise. So this coefficient is called the homotopy coefficient system, and this coefficient system plays an important role to understand the topological whatever conjecture. That is a totally combinatorial way. And yeah, so I'll talk something about now we have the G space. Now we have the coefficient system. So it's more natural to talk about the chains and homology. So what are the chains? So everything here we view as a functor. Okay, as a functor from orbit category to abelian groups. So a chain complex or chain coefficient system, rather in our terminology, is something which will act on the orbits and gives you the chains on the fixed point. So if anybody don't know about what is the chain is, then I can explain in one line. That is, chains is something it's like I can give you some example from the previous talk. So you have the triangulation of this space, this fixed point set, and you choose the triangle. It's like not like triangulations. Like whenever you have something, you have triangles. If you have a surface, whenever you are higher manifold, you not only have the triangles, you have the tetrahedron and also higher dimensional simplex. So here in the fixed point, we are saying, so if this is a two-dimensional surface, then the C2 is nothing but the number of triangles used to explain this space, this G space, or this non-equivalent space. Like for sphere, as Pradipta said, the number of triangle you used to explain S2 is, I guess, 4, right? Yes, it is. So that means that guy is something copies of 4 ring of integers. So it is z power 4 in that example, but it is not the same. It is some kind of analogy I try to build up to understand these things in rather easy manner. So this is some kind of cell that I said, like cells are the copies of a disk, in geometry people do with the triangles, but in topology people do it anything, because topology is nothing but the Robert seat geometry. So you just take the disk and think it is a triangle and do the same thing there. You will get a cells here. So this is the number of n cells or number of n dimensional triangle, in rather other sense n simplices, number of n simplices here. Okay, so this is somehow called singular n chains. And just forget about singular. Singular means you just you are allowing not only the affine maps, also the continuous maps. So it may have the singular points. So just forget about these things. Okay, so once you have this thing, then we definitely can talk about the boundary maps. So you take one chains and restrict it to the boundary of the simplex. So as I explained, what is the chain? It's chain is it is an free abelian group generated by the number of simplex of this dimension. So you can restrict yourself on the boundary of the simplex. What you get is the n-1 simplex and its linear combination. So you have a canonical boundary map over the fixed points. And once you have the boundary map that forms a chain, that means if you for each n you have such kind of map, and from here you have d delta n-1, and if you compose the consecutive one, it will gives you 0. That is the definition of chain. So once you have the chain, you can talk about the cochains. So for cochains, cochains is some kind of dual object in the category of chains, where you have to fix some coefficient system that I explained. It is as a contravariant functor from the orbit category to the abelian groups. And then this is also the chain coefficient system is also a contravariant functor from orbit category to abelian groups. So now we can talk about maps between them. So this is nothing but the maps between these two functors, and it produce the cochains over the G space X with coefficient system M, and it also dualize the boundary map. So you have the boundary map here delta. You can so it's called the partial, and now the delta is the dual of the partial. And now you just take the kernel and image and cosine it out, because if you take the consecutive 2 of this guy, delta n compose delta n-1, that will gives you 0. So the image will sit inside the kernel, and then you can talk about the quotiented thing. So the cohomology of x with coefficient, this m should be the m underline, sorry for the typos, all this m, and is equal to the kernel quotiented by the image, and this guy is called the Braidon cohomology of x with coefficient in this m with the underline. It's a typo. Okay, fine. So now I'll say, so this is the whole structure of Braidon cohomology theory we will going to use, and we now understand what is the statement of Trademark conjecture. Now I want to make a bridge between them. So what is the meaning of this guy? So I try to understand if a map does not satisfy the topological Trademark conjecture, what is going to happen for this map. So before going to that, I just want to explain some one basic definitions from the simplicial complex theory, that if you have a simplicial complex. So what is the simplicial complex? I thought I should explain this one, but already Pradipta explained in his talk by saying the triangulation. So this is the same concept of triangulation, like it's a bunch of simplex put together, and you just you take the intersection of any two of them. If it is the lower simplex or it's a face sharing them, then it should be the inside the collection, otherwise you have to throw them. So this is the same definition in a generalized sense for triangulations of surface or manifold. Okay, so it's some generalized simplex, or you can think that this is a collection of simplex with certain way of attachment. Okay, so you have simplex, simplicial complex, and you can talk about the n-fold disjoint join. What is that? You just take the the face of this simplicial complex K, and these faces should be pairwise disjoint like that, and you take this kind of addition rule, and remember this addition is some kind of tautological addition. It's not, you can see this addition because this is not the vector space, so it's some kind of tautological things is going inside here. And you have seen these things, like whenever you have a circle and you take 2 copies of circle and you do the actual join, you will get the 3-dimensional sphere. So it's similar kind of thing is going here, but here something is called the dilated sense. So you have to put this extra conditions. So this extra conditions stand for this delta 2. Okay, any 2 of them are disjoint. So you have this kind of construction, and here the sigma i's are the non-empty faces of the simplicial complex. And the most important thing is this guy is comes with an free action. Free action means not, the action is not free, sorry, the action is not free, but it comes for free. Okay, so this guy has the action of symmetric group of order n factorial. So sigma is sigma symmetric group with order n factorial. And the thing is, that means you always have an action of the symmetric group. So we can talk about the equivariant map, which is a symmetric group invariant. So we will see these things in a minute. Okay, so I just put the name disobeying. That means a guy which is not obeying all this result that I said. That means if your map F is a disobeying, that is, it violates the topological Trademark conjecture, what is going to happen? So it's very tricky that you can do this n-fold deleted join operation, and you'll get something. Okay, that something map which is equivalent. So before that, just one note for what is the meaning of violating the conjecture. So we say that a map, if you have a map, it says that conjecture says that whenever you have a map, then you always find certain collections of n-fold partition of the faces, so that the image intersection of the image is non-empty. So here it's exactly opposite. So for every n tuples, you with a pair of disjoint faces, and the intersection should be empty. So if something is violating the conjecture, it will satisfy this guy. So once you have this kind of function which satisfy this property, you can do the deleted join, because these all guys are pairwise disjoint. So we can talk about the deleted join. So you use the deleted join construction to get a map from this complicated expression to this big Euclidean space. Okay. So this, but this guy comes with, so what is the definition of this guy? So in left hand side, the elements look like this, and you just do this kind of assignment to get a map. But this map has a very good property. That thing is, this map comes with a sigma n, that is symmetric group action. So we can talk about the homotopy theory for symmetric groups, and we can understand that this a map when it is a disobeying. Okay, so getting the right map. So this is getting the all about the getting the right map. So you have this map. So you forget about this crazy definition. You just see this you have this map, fine. Now you just see this definition, that is fine, and you try to understand it satisfies this relation. That is enough for the whole data. So now you just take some subspace in your codomain. So the subspace, so it is some kind of n cross d plus 1 matrices, right? So it is so all the matrices where the rows are equal. Okay, so you can view these as a matrix. So it's all matrices where the rows are equal, and we know you can flip each, sorry, you can permute each row using the symmetric group action, and it will gives you nothing because all the rows are equal. So you will get reached to a same matrix. So that means this guy is a sigma n equi-invariant. That means it is not changing under the action of sigma n. Okay, so if you have equivariant map and you have a subspace which is not bother about the action, so like this guy is not bother about the action, then you can delete that guy. It's not, so that means you don't need this guy to be inside your codomain of the map, so you can delete this guy. So but before deleting this guy, you have to make sure that this guy is not affecting the image. So you can check the image of this big map from this deleted joint to Euclidean space is not sharing anything with our this invariant set. So why this is so? It's very basic. If you have a common point, that means you have this kind of situation satisfying, then this guy is, so all these guys are same, then you can choose one point in each simplex which have the same value, because whenever all these values are same, that means all this simplex has a common point. Like you can talk about 1 by n of y1 and equal to 1 by n of yn, and this guy will gives you a common point in the intersection, but we assume that intersection of each simplex, disjoint faces should be empty, so it will gives you a contradiction. Therefore this is a non-empty, it is an empty intersection. So now you can delete this guy because it's not bothering into the image, also it's not bothering the action. So this is a extra part inside the codomain, so we'll delete this guy. So first of all, just think this is our map f star n sigma delta 2, this first map, and we have deleted this invariant thing because it's not sharing anything. Now you have a basic trick from linear algebra. You can restrict everything to the, you're deleting something, and that means this is a invariant subspace. It is it has you can talk about the invariant complementary part inside this big vector space, or inside this big yeah, you can think of vector space or matrix or collection of all matrices. So this guy gives you the complementary part, and because it is a vector subspace, it is also shares 0, so you should have to remove the common 0 from this dj. So it will the complement of the vector space dj gives you a continuous maps to the d perpendicular minus 0. So once you have a vector space minus 0, you can talk about the norm of the vectors, and you can send each vector to vector quotiented by the norm. So v factored by norm v. So that gives you norm 1 vectors. That means you will land inside the sphere inside the vector space d perpendicular. Now look at the what is the perpendicular of this subspace. It's very easy to see. Like whenever you have all the columns, all the rows are equal, if you take the perpendicular, that means you have to take vectors which is the inner product with this guy. The inner product comes from the inner product induced from this Euclidean inner product space, and that should be 0, and that means all the sum of the columns or sum of the rows should be 0. So we have to we're getting something, some vector space where the sum of the row or sum of the column is 0 depending on the choice of this. So we choose Wn as a subset of Rn where the sum of each member is 0, and so this guy has a dimension d minus 1, and you remove the 0, that means it is dimension d as a vector space. Then you can talk about the complement, and complement gives you by this vector subspace. Okay, so that means you have d plus 1 copies of this guy. Okay, fine. But funny thing is we are not losing any equivariancy in throughout this 4 map. All this 4 map preserve the equivariance relation. That means all these 4 maps respect the action by sigma n. Okay, fine. So you get a map. So what is the now I'll try to summing up the things. So the thing is, so you use these things to get a map from here to this big n-fold disjoint union, n-fold join to a sphere in a very special inside a representations. It is a very special representation inside the symmetric group. Okay, so it is some representation of the symmetric group and inside the sphere of that. Okay, so the upshot is like this: you get a map, the all composite. Now you have to identify these things. So whenever you have a simplex, a standard simplex, you can talk about its vertex. So a simplex always comes with a if your simplex is n dimensional, it has n plus 1 vertex. So if you do the if you do the join, topological join that I just explained, like n-fold join, you'll get the whole simplex. So the simplex data is nothing but the join of all vertices. So that means you have this simplex is just one point, and joining the one point as this number plus 1 times. Okay, so this whole picture gives you this identification. But note that this identification is very interesting. Here you get numbers 1 to n, and this number also has action by symmetric groups by sigma n by permitting the numbers. That means we are not losing the equivariant action throughout all the process. This is important, that we are not losing the action, and you can see these actions is respect the action in the left hand side. So what is the upshot? So you start with some map f which violates the topological Trademark conjecture, and then it gives a sigma and equivariant map from this join to a big sphere. But remark is non-existence of this map will gives you the the positive result to the conjecture. But warning, if you get a map like this, it doesn't say anything about the conjecture is false or not. Okay, fine. So now I'll say something of the weaker conjecture and the Ojaidian's question. So a natural question is that if your n is, I forgot to mention you something, this conjecture, whatever I said about the conjecture, is this conjecture is true once your n is prime power. Okay, so people don't know anything about what is the case for if your this n is not prime power. So it was open until 2015, mid of 2015, and then we just consider this kind of thing, like you should take your n is not prime power and you start with some continuous map where I impose this condition, like n is not exactly the optimal number, it is bigger than the optimal number. Okay, then the question is, are there any n disjoint faces whose image have the common point? The same thing, same questions for little, it's not weaker in that sense, but we are not taking the optimal number, we are taking all numbers bigger than optimals. Okay, now a similar techniques what people do in Trademark case, we will get some map from here, the big join to a big sphere, as I explained in one slide back. So this leads to a famous question by Ojaidian in around 1980s, that what you are saying about all equivariance with respect to the symmetric group. What happens if your symmetric groups, if you restrict your symmetric groups to any subgroup of it? So take G be any subgroup of the symmetric group and you ask the same question. So this guy is the representation, restriction of the representation W. So you ask the same question, and mind that you have this condition of non-prime powerness and your n is bigger than the optimal number. So under this hypothesis, do you have a way out to understand this kind of equivariant maps? So we consider this kind of question and we try to answer this question. So let's assume EG is the model for the contractible G space. Okay, so contractible G space means, as I told you, what is the homotopy is. Homotopy means a deformation from one map to another map. So a contractible space means here you can deform the identity map to a constant map. Okay, so identity map or homotopic to a constant map. So you always have a contractible space throughout U, because it's just, you can think it as a point or a disk, anything. But there are specific models of free G space which are contractible. That means it has G actions and the action is free, it has no fixed point, and it is contractible. So what is the basic construction one can follow? Like, you start with some group G and you can do the topological join operation infinite times. For example, I can tell you, like, you start with 2 points as your Z mod 2 cyclic group with order 2, and you can join them once, like Z mod 2 join, that join is the star, and Z mod 2, you will get circle, you will get 3 times, you will get sphere, and if you do the same process for infinite number of times, you will get a sphere inside a infinite dimensional Euclidean space. But we know that infinite dimensional sphere is a contractible guy. So that is a model for the cyclic group with order 2. And in general, we are taking EG as a model for the contractible free G space. And we proved if n is not a prime power and d is bigger than 1, then there exists a CN equivariant map from this contractible model to that sphere, that big representation sphere mentioned by Ojaidin. Now the point is, it's not saying something about this thing, right? But look at this guy. This guy has a symmetric group action given by the permutation, but if you restrict the action to the cyclic subgroup inside the symmetric group, the action is free. So we understand that ECN is a free universal object in the contractible sense. Therefore, it always contained this kind of object inside ECN. This kind of object is always sit inside ECN. If your n tends to infinity, that is actually model for ECN. Okay, fine. So proving this thing is a much more harder, and the Ojaidin's result is a corollary of this guy. So this is why this is much more harder, because we are proving something on the infinite complex. So it will gives you result for any n. It's any n bigger than optimal dimension. So proving these things is equivalent to proving all this conjecture in weak sense. So B, we also prove the result for the Ln. What is the Ln? Ln is the product of elementary abelian groups, and Cn stand for the cyclic groups. And we also prove the similar result for a dihedral group where n is odd number. And the good thing is here, this guy has a different structure. It's not exactly the same like that contractible free G space. The action here is not free. It is fixed under the action of subgroup H. H is the subgroup with order 2 inside Dn. So we can determine, we understand the fixed point theory, like whenever you have a G space, it can be determined by the fixed point that I explained in first few slides. So if you want to define this guy, it is enough to define for its fixed point. So the fixed point says that guy will be a homotopic to point that is contractible if your K is either identity group of order 2, or it is empty if otherwise. Okay, so this is some explanation for this object, but all this consecutive 3 result says that the Ojaidin's theorem, Ojaidin question has a negative answers for these groups. Also, it says that you cannot prove your topological Trademark conjecture using this guy. At the end, we also showed that the Trademark conjecture is false once your number n is not equal to prime power. Fine. So what is the sketch of the proof? It's very involved, but I just want to figure out 2 or 3 lines. Like, first of all, we build some diagram like this, where these are the all topological space, and we want to lift the map from B to E, and lifting some map is something in topological spaces called the obstruction theory. So we want to calculate the obstructions, and the obstructions lies in the cohomology group like this that I explained, where the coefficient system are very special that I explained, like it's the homotopy coefficient system, and here the obstruction all are lies bigger n bigger than equal to 2. So this plays the role of coefficient system, and where f is the pullback of a point here. This is called the fiber of this bundle. Okay, so once you have these things, so we've computed this whole cohomology group for these objects are very critical objects. So for some mapping objects, we computed that thing, and we check this all cohomology groups, and in particular the obstruction to lifting the map to the top vanishes for the group G equal to cyclic group, elementary product of elementary abelian groups and the dihedral groups. Fine. Yeah, so I think this is what I would like to say. Thanks to all. This is the end of my talk, and you are free to ask any question. Yeah.
Thank you, Dr. Surojit Ghosh, for unique speech on topological space and topology. Is there any question, Somen?
No.
I have a
Surojit-
question to Dr. Surojit Ghosh.
Okay.
Yeah.
I have a question. Actually, I am not very familiar with the topology because I'm the student of applied mathematics. So, can you explain the fact that you have said in one place that when two circles in 2 dimension are joined, we get a sphere in 3 dimension? Can you explain the fact?
Yeah, that I can explain to you. Like, basically, it produces an homeomorphism. Like, what is the meaning of joining? I can explain in a shorter dimension that you can just take 2 points. Okay, take 2 points and take another 2 points disjointly, and whenever we say join, that means you are joining this vertex with this one and this vertex with this one. Okay, so we are joining like this. So whenever you join this, you start with 2 points and join with itself, it will give you one circle, right? It's similar to circle. It's topologically circle. Now you start 3 points, like another 2 points in opposite 2, and join with the all the circle. So it will give you sphere. So whenever you do the join, okay, whenever you do the join, it will increase the dimension by extra 1. Okay, so I can explain for the circle also. You can do the circles, but it's very hard to explain by, you have to do the homeomorphism. It's a four dimensional object. I can't do it inside. Yeah, it's hard to explain.
Okay, thanks. Many thanks. We have come to the end of our program, and I am requesting my colleague and assistant professor of mathematics in Nagar College, Soumen Pradhan, to give the vote of thanks in this context.
Thank you. Honorable Principal Sir, respected IQSC coordinator Sir, respected Jaideep Sir, our eminent speakers, and all the participants. Good afternoon. It's my privilege to have been asked to propose a vote of thanks. On behalf of Nagar College, I, Mr. Soumen Pradhan, take this opportunity to propose vote of thanks to those who have directly and indirectly contributed to this webinar on one-day international webinar on recent trends in mathematics, organized by the Department of Mathematics, Nagar College. A very hearty vote of thanks to the honorable delegates who blessed us with their presence and took out valuable time of your busy schedule. I would like to thank our honorable principal, Sri Soumen Chakraborty sir, for delivering the welcome address speech and for being our backbone in our endeavor and constantly motivating and inspiring us. Your dedication and commitment to our college really inspiring us. And also, I would like to thank Dr. Sudipta Sayu, IQSC coordinator Nagar College, to motivate us and even guide us to organize such a successful webinar. Now, first of all, I would like to thank Dr. Sukhendu Kaur sir, Associate Professor, Department of Mathematics, University of Jadavpur, India, for his excellent speech on Introduction to Ternary Structure. And I think really we all enjoy his lecture. And then I would like to thank Dr. Pradeep Majhi, Assistant Professor, Department of Mathematics, University of Calcutta, India, for his effort towards the Gauss-Bonnet theorem and its application. And finally, I would like to thank Dr. Surjit Ghosh, University of Haifa, Israel, for his excellent explanation and such a beautiful presentation on Trademark conjecture from equivariant homotopy viewpoint. I think everyone enjoy his awesome presentation. And I want to tell one more thing about Dr. Surjit Ghosh. He was received the most honorable Ramanujan Fellowship, and we are very thankful to all the respected teachers for their valuable guidance and contribution. Without their supervision and encouragement, we are not able to give our best. So I must mention our deep sense of appreciation for Dr. Manik Biswas and Mr. Tafikur Rahman for their excellent work and hosting this beautiful event. We are really enlightened with your knowledge and presence. A special thanks to the organizing committee, teaching and non-teaching staff for their unflinching support and coordination. With these warm words and a kind message, we move to the end of today's webinar. Lastly, I would like to thank to all the participants to participate in this international webinar. Have a nice day. Over to Jaidev sir.
We have come to the concluding part or end of the program. I express my thanks and gratitude to the eminent speakers, all the participants, and our students, and our principal sir and Dr. Sudipta Shah, IQAC coordinator, in this context to make successful program organized by Department of Mathematics, Nagar College. Thank you.
Thank you.
Okay.